Welcome to the Whispering Universes channel, where tonight we embark on perhaps the most mind-expanding journey science has ever offered us. As you settle into this moment, breathing slowly and deeply, prepare to dissolve the boundaries of everything you thought you knew about reality itself. Imagine, if you will, that this very moment you reading these words, the air moving in and out of your lungs, the thoughts forming in your mind, is just one thread in an infinite cosmic tapestry. Every decision you've ever made, every path you've chosen, every word you've spoken has spawned countless other realities where different choices unfolded. The multiverse hypothesis suggests that our universe, vast beyond comprehension, with its hundreds of billions of galaxies, might be nothing more than a single bubble floating in an infinite ocean of existence. This isn't science fiction whispering to us from the pages of imagination. This is cutting-edge physics, born from the deepest mathematical explorations of quantum mechanics and cosmology. The greatest minds of our time, physicists who've dedicated their lives to understanding the fundamental nature of reality, are telling us something extraordinary. We might not be alone in the way we always assumed. The multiverse concept emerges naturally from our most successful theories. When we peer into the quantum realm, we discover a reality that defies our everyday experience. Particles exist in multiple states simultaneously until observed. Information can be transmitted instantaneously across vast distances. The very act of measurement seems to create the reality we observe. These aren't philosophical musings, they're experimental facts that have been verified thousands of times in laboratories around the world. But here's where it becomes truly breathtaking. If quantum mechanics is correct, and if the mathematics that describe our universe are complete, then every possible quantum event that could happen does happen, just in different universes. Every time an electron chooses which slit to pass through in a double-slit experiment, reality branches. Every time a radioactive atom decides whether to decay in the next moment, new worlds split off from our own. Consider the profound implications. Right now, as you listen to these words, there might be infinite versions of you experiencing this same moment, slightly differently. Perhaps in one universe, you chose to listen to this video tomorrow instead of today. In another, you never discovered this channel at all. In yet another, the history of physics unfolded differently, and this video discusses entirely different theories about the nature of existence. The multiverse hypothesis challenges our most basic assumptions about uniqueness and specialness. If infinite realities exist, are we just one random configuration among countless others? Or does the very fact that we can contemplate these questions make our particular universe special? These are the kinds of profound questions that arise when we take seriously the possibility that our reality is just one note in an infinite symphony of existence. Tonight, we'll explore how this extraordinary idea emerged from the mathematics of quantum mechanics. We'll journey through the elegant theories that suggest infinite universes bubbling into existence, each with their own unique physical laws and possibilities. We'll examine the evidence, tentative but growing, that these other realities might actually exist. And we'll grapple with the philosophical implications of living in a cosmos where every possibility is realized somewhere. As we begin this exploration, let your mind expand beyond the familiar boundaries of space and time. Tonight, we're not just learning about physics, we're discovering our place in the vast, possibly infinite dance of realities. The mathematics may be complex, but the wonder is simple. You are part of something unimaginably magnificent, and every moment brings new possibilities into existence. Let the gentle current of cosmic possibility carry you forward as we dive deep into the mystery of infinite realities. In the autumn of 1957, a young Princeton graduate student named Hugh Everett III submitted a doctoral thesis that would fundamentally challenge how we think about reality itself. The title was deceptively modest, On the Foundations of Quantum Mechanics, but buried within its mathematical formalism was an idea so radical that most physicists initially dismissed it as science fiction. Everett proposed that every time a quantum measurement occurs, the universe doesn't choose a single outcome. It splits into multiple realities, each containing a different result. To understand why this idea was so revolutionary, We need to travel back to the early 1900s, when quantum mechanics was first emerging from the minds of physicists like Max Planck, Albert Einstein, and Niels Bohr. These pioneers discovered that at the smallest scales of reality, particles behave in ways that completely violate our everyday intuition. An electron, for instance, doesn't have a definite position until we measure it. Instead, it exists in what physicists call a superposition, simultaneously occupying multiple locations with different probabilities. The most famous illustration of this quantum strangeness is Schrödinger's thought experiment with a cat in a box. Erwin Schrödinger, frustrated with the implications of quantum mechanics, imagined a cat sealed in a box with a Geiger counter, a radioactive atom, and a poison mechanism. If the atom decays, the Geiger counter triggers the poison and kills the cat. If it doesn't decay, the cat lives. According to quantum mechanics, before we open the box, the atom is in a superposition of decayed and not decayed states. This would mean the cat is simultaneously alive and dead until we observe it. Most physicists in the 1920s and 1930s solved this paradox by adopting what became known as the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. They argued that the act of measurement causes the quantum wave function to collapse into a definite state. The cat becomes either alive or dead when we open the box and observe it. Before that moment, the question of its state is simply meaningless. But Everett saw a different possibility. What if the wave function never actually collapses? What if both outcomes, the cat alive and the cat dead, are equally real but exist in separate parallel universes? When we open the box, we don't cause collapse. Instead, we become entangled with one particular outcome, while other versions of ourselves in parallel universes observe different results. This many worlds interpretation, as it came to be known, suggests that reality is constantly branching. Every quantum event creates new universes. The radioactive atom doesn't randomly choose whether to decay, it both decays and doesn't decay, creating two separate realities. We experience only one branch of this cosmic tree, but all branches are equally real and valid. Everett's advisor, John Wheeler, was initially intrigued, but ultimately couldn't bring himself to fully embrace such a radical departure from conventional thinking. The physics community of the 1950s was even more resistant. How could anyone seriously propose that trillions of universes are created every second? Where do all these realities go? How can we possibly test such an extravagant theory? For nearly 2 decades, Everett's interpretation languished in obscurity. Discouraged by the lack of acceptance, Everett left academic physics entirely, eventually working for the Pentagon on nuclear strategy. His revolutionary idea might have died with his departure from physics, forgotten as an interesting but untestable speculation. But in the 1970s, physicist Bryce DeWitt at the University of North Carolina rediscovered Everett's work and began promoting it with evangelical fervor. DeWitt realized that the many worlds interpretation wasn't just a philosophical curiosity, it was the most logically consistent way to understand quantum mechanics. If you take the mathematics of quantum theory seriously, without adding arbitrary assumptions about wave function collapse, the many worlds interpretation emerges naturally. DeWitt's popularization efforts coincided with growing dissatisfaction among physicists with the Copenhagen interpretation. The more scientists thought about wave function collapse, the more mysterious it seemed. What exactly constitutes a measurement? When does collapse occur? Why should the universe behave differently during observations than at other times? These questions had no satisfactory answers within the Copenhagen framework. The many worlds interpretation elegantly sidesteps all these problems. There is no collapse, no arbitrary boundary between quantum and classical behavior, no special role for consciousness or measurement apparatus. The Schrödinger equation, the fundamental equation of quantum mechanics, simply evolves forward in time, creating an ever-branching tree of realities. By the 1980s and 1990s, attitudes toward many worlds began shifting dramatically. Surveys of physicists showed growing acceptance of the interpretation. Renowned scientists like Stephen Hawking, Murray Gell-Mann, and David Deutsch became vocal advocates. The interpretation gained theoretical support from developments in quantum field theory and cosmology. Today, the many-worlds interpretation is considered one of the leading explanations for quantum mechanics. While we still can't directly observe parallel universes, the interpretation makes testable predictions about quantum interference effects and the behavior of quantum computers. Some physicists argue that quantum computers actually harness the computational power of parallel universes to solve certain problems exponentially faster than classical computers. As we continue our journey tonight, we'll explore how this seemingly outrageous idea that every quantum event creates new realities has become not just scientifically respectable, but increasingly necessary to explain the deepest mysteries of existence. Hugh Everett III's radical vision has grown from a rejected thesis into a cornerstone of modern physics, suggesting that we live in a cosmos far stranger and more magnificent than anyone previously imagined. Descend with me now into the deepest layer of reality, smaller than atoms, smaller than protons and neutrons, smaller than quarks themselves. Here, at a scale so tiny that it defies imagination, the Planck length, just 10 circumflex, -35 meters space and time, lose their familiar meanings. This is the quantum foam, a seething, bubbling froth of possibility, where virtual particles appear and vanish in the blink of an eye, and where the very fabric of space-time itself writhes and fluctuates according to the principles of quantum uncertainty. It was John Wheeler, the same physicist who mentored Hugh Everett, who first envisioned this microscopic realm in the 1950s. Wheeler realized that Heisenberg's uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a particle with perfect precision, must apply not just to matter and energy, but to space and time themselves. At the smallest possible scales, the smooth fabric of Einstein's space-time becomes a violent quantum storm. Picture, if you can, looking at the surface of a calm ocean from an airplane flying at high altitude. The water appears perfectly smooth, a mirror-like expanse stretching to the horizon. But descend closer, and you begin to see waves and ripples. Closer still, and individual drops of spray become visible, dancing and colliding in chaotic patterns. The quantum foam is similar. Our everyday experience of smooth, continuous space is like the view from the airplane. But reality at the Planck scale resembles the molecular chaos of crashing waves. In this quantum foam, the energy of empty space itself fluctuates wildly. What we think of as vacuum-empty space containing nothing is actually a seething sea of activity. Virtual particles constantly appear in pairs, borrow energy from the quantum vacuum, dance briefly in existence, and then annihilate each other, paying back their borrowed energy before the universe notices the debt. These aren't just theoretical constructs. Their effects can be measured in the laboratory through phenomena like the Casimir effect, where two metal plates placed very close together in vacuum experience a tiny but measurable attractive force due to virtual particles. But here's where the story becomes truly extraordinary. If the quantum foam can create virtual particles that briefly borrow energy from empty space, what happens if the fluctuations become large enough? What if, instead of tiny virtual particles, the foam produces something much bigger, an entire universe? This possibility emerged from the work of cosmologists, studying the very earliest moments after the Big Bang. In the 1980s, physicists like Alan Guth and Andre Linde developed inflation theory, which suggests that our universe underwent a period of exponential expansion in its first fraction of a second. During this inflationary epoch, quantum fluctuations in the fabric of space-time were stretched to cosmic scales, becoming the seeds for galaxies and large-scale structure we observe today. But if inflation could happen once, why couldn't it happen again and again? Linde and other theorists realized that inflation might be an eternal process. In some regions of space, inflation ends, and universes like ours emerge, filled with matter and energy, cooling into stars and galaxies. But in other regions, inflation continues, spawning new regions where inflation ends, creating more universes. The process never stops. It's inflation all the way down, or rather, all the way up, creating an infinite fractal tree of bubble universes. Each bubble universe emerges from quantum fluctuations in the foam, carrying with it potentially different physical laws and constants. The strength of gravity, the mass of electrons, the rate of radioactive decay, all these fundamental parameters that determine how physics works in our universe might be random outcomes of quantum fluctuations in the foam. Some bubble universes might have stronger gravity, causing them to collapse before stars can form. Others might have weaker nuclear forces, preventing the synthesis of complex elements. Our universe, with its seemingly fine-tuned constants that allow for the existence of atoms, molecules, and life, might be just one lucky bubble among countless others. The mathematics describing this process are beautiful in their simplicity. The same equations that govern the virtual particles popping in and out of existence in your laboratory also describe the birth of entire universes. Scale invariance, the idea that the laws of physics look the same at different size scales, suggests that what happens in the quantum foam might be fundamentally similar to what happens during cosmic inflation. Universes might be born from vacuum fluctuations, the same way virtual particles are, except instead of lasting for a tiny fraction of a second, they persist and grow into vast cosmos containing billions of galaxies. Modern attempts to understand the quantum foam have led to even more exotic possibilities. String theory, our most ambitious attempt to unify quantum mechanics with general relativity, suggests that, at the Planck scale, space itself might be made of tiny vibrating strings or membranes. These fundamental objects, smaller than any particle we can imagine, vibrate in complex patterns that give rise to all the forces and particles we observe. Different vibration patterns create different types of particles, like different notes played on a cosmic violin. In this stringy quantum foam, the possibilities for universe creation become even richer. Brane's higher dimensional surfaces in the mathematical space of string theory might collide and create Big Bang events. Loops of string might expand into cosmic structures. The foam itself might exist in multiple dimensions beyond the 3 spatial dimensions we experience, with our universe confined to a particular slice of this higher dimensional space. Recent developments in quantum field theory have revealed even deeper connections between the quantum foam and consciousness itself. Some interpretations suggest that the act of observation or measurement might play a fundamental role in determining which virtual particles become real, which fluctuations grow into universes, and which possibilities collapse into actuality. If true, this would mean that consciousness and the quantum foam are intimately connected, with awareness itself participating in the creation of reality at the most fundamental level. As we breathe slowly and let these ideas settle into our minds, we begin to glimpse the truly vast scope of existence. The quantum foam beneath our feet, beneath our atoms, beneath the very concept of space and time, is constantly creating new possibilities. Each fluctuation, each virtual particle, each tiny quantum event participates in an infinite dance of creation that has been going on since before time began and will continue long after our universe grows cold and dark. We are not separate from this process. We are part of it, expressions of the quantum foam's endless creativity, brief patterns of awareness that have emerged from the cosmic dance to contemplate their own origins. Let us now ascend from the quantum foam into the pristine realm of mathematical description, where reality reveals its deepest secrets through elegant equations and infinite dimensional spaces. Here, in the language that nature itself seems to speak, we discover that the multiverse isn't just a wild speculation, it's a natural consequence of taking our most successful theories seriously. At the heart of quantum mechanics lies a mathematical object called the wave function, represented by the Greek letter psi. This isn't just an abstract symbol, it's arguably the most important equation in all of physics, containing within its mathematical structure all possible information about a quantum system. When Erwin Schrödinger first wrote down his famous equation in 1926, he probably didn't realize he was describing not just the behavior of particles, but the very architecture of reality itself. The wave function exists in what mathematicians call Hilbert space, an infinite-dimensional mathematical arena where every possible quantum state corresponds to a point. Imagine trying to describe the position of a dot on a piece of paper. You need two numbers, representing coordinates on the x and y axes. To describe a point in three-dimensional space, you need three numbers. But to describe the quantum state of even a single electron, you need an infinite number of coordinates in Hilbert space, each representing the probability amplitude for finding the electron in a particular state. Now scale this up to an entire universe. The universal wave function, the mathematical description of everything that exists, lives in a Hilbert space so vast that it encompasses every possible arrangement of every particle, every possible outcome of every quantum event, every possible history the universe could have followed. This space contains not just our universe, but all possible universes existing simultaneously as different points in this infinite mathematical landscape. The beauty of this mathematical framework becomes apparent when we realize that the Schrödinger equation doesn't pick favorites. It treats all possible quantum states democratically, evolving them forward in time according to the same mathematical rules. There's no special mechanism that selects one particular outcome and discards the others. Instead, all possibilities continue to exist and evolve, each following its own branch of the universal wave function. To understand how this branching works, consider the mathematical concept of superposition. In the familiar world of classical physics, a coin is either heads or tails. But in quantum mechanics, a quantum coin can exist in a superposition of heads and tails simultaneously, with specific probability amplitudes for each state. The total wave function is a linear combination of all possible states, weighted by their probability amplitudes. When quantum systems interact, when measurements occur, when particles collide, when any quantum event takes place, the mathematics of superposition becomes more complex, but follows the same principles. The wave function doesn't collapse into a single outcome. Instead, it branches, with each possible outcome continuing to exist in the mathematical structure, but becoming isolated from the others through a process called decoherence. Decoherence theory, developed in the 1970s and 1980s by physicists like Wojciech Jurek and others, provides the mathematical framework for understanding how classical reality emerges from quantum possibility. When a quantum system becomes entangled with its environment, the different branches of the wave function rapidly become isolated from each other. They still exist mathematically, but they can no longer interfere with each other. This is why we experience a definite, classical reality rather than quantum superpositions in our everyday lives. The mathematics reveals something profound. What we call measurement or observation isn't fundamentally different from any other quantum interaction. When a photon hits your retina, when a Geiger counter clicks, when any quantum system interacts with any other quantum system, the universal wave function branches. The mathematics treats your consciousness exactly the same way it treats any other quantum system, as part of the universal superposition, splitting along with everything else. This mathematical democracy extends to the concept of probability itself. In a single universe, quantum mechanics provides only probabilistic predictions. We can calculate the likelihood of different outcomes, but can't predict exactly what will happen. But in the many worlds framework, these probabilities take on a different meaning. Every outcome with non-zero probability actually occurs in some branch of the wave function. Probability becomes a measure of how much of the universal wave function is devoted to different outcomes. The mathematical elegance goes even deeper. The squared amplitude of the wave function, what quantum mechanics tells us, represents the probability of an outcome in our single universe, corresponds directly to the measure or thickness of that branch in the multiverse. Outcomes with higher probability amplitudes correspond to branches containing more observers, more copies of ourselves experiencing those outcomes. This leads to the profound realization that mathematics itself might be the fundamental substrate of reality. Max Tegmark's mathematical universe hypothesis suggests that mathematical structures don't just describe reality, they are reality. Every mathematically consistent structure exists as a universe, and we find ourselves in this particular mathematical structure because it's one that can support observers complex enough to contemplate their own existence. The implications ripple outward through every area of physics. Quantum field theory, which describes the behavior of particles and forces, becomes a theory of interacting fields across all possible universes. The standard model of particle physics, with its intricate mathematical structure describing the fundamental forces and particles, represents just one slice of a much larger mathematical reality containing all possible physical laws. Even general relativity, Einstein's geometric theory of gravity, takes on new meaning in this mathematical multiverse. Space-time isn't just the stage on which physics plays out, it's one particular mathematical structure among infinitely many. Different universes might have different numbers of spatial dimensions, different geometries, different relationships between space and time. As we let these mathematical vistas settle into our awareness, we begin to appreciate the profound beauty of existence. We are patterns within patterns, mathematical structures, contemplating mathematical structures, conscious arrangements of quantum fields, becoming aware of the infinite mathematical landscape that contains us. The equations that describe reality aren't cold, abstract symbols. They're the deepest poetry the universe knows how to write, and we are both the readers and the verses in this cosmic mathematical epic. The numbers dance, and we dance with them, carried forward by the elegant currents of infinite possibility. As we journey deeper into the landscape of infinite realities, we encounter a brilliant taxonomist of the impossible, Max Tegmark, a cosmologist at MIT, who has mapped the territories of the multiverse like a cosmic Lewis and Clark. In the early 2000s, Tegmark realized that physicists were discussing at least 4 fundamentally different types of multiverse, each emerging from different aspects of our theories, each offering different levels of strangeness and wonder. Tonight, we'll explore each level, ascending through increasing degrees of abstraction until we reach a vista so vast it encompasses every possible mathematical structure that could ever exist. Level I, beyond the cosmic horizon. We begin our ascent with the most conservative and perhaps most certain type of multiverse, one that emerges simply from the observable fact that our universe appears to be infinite in size. Look up at the night sky, and you're seeing only a tiny fraction of what exists. Light from distant galaxies has had only 13.8 billion years to reach us since the Big Bang, creating a sphere of visibility called our observable universe. But beyond this cosmic horizon lies more space, more galaxies, more stars, possibly extending forever. If space is truly infinite, and if matter is distributed roughly uniformly throughout this infinite expanse, then something remarkable must be true. Every possible arrangement of matter within a finite volume must be repeated infinitely many times. This is a consequence of basic probability theory applied to infinity. With infinite space and finite ways to arrange atoms within any given region, exact repetitions become not just possible, but inevitable. This means that somewhere beyond our cosmic horizon, there's another planet exactly like Earth, with another version of you reading these exact words at this exact moment. The distance to your nearest identical copy depends on how precisely we define identical, but calculations suggest it's roughly 10 to the power of 10 circumflex 29 meters away, a number so large it defies comprehension. But in an infinite universe, such incomprehensible distances are just addresses in the cosmic neighborhood. Even more mind-bending, there are infinitely many versions of you out there. Some are reading this sentence, but thinking slightly different thoughts. Others made different choices throughout their lives. Perhaps one version chose a different career, another moved to a different city, yet another never discovered this channel at all. The level I multiverse is populated by infinite variations of every possible person living out every possible life. Level 2. Bubble universes with different physics. Level 2 takes us into far stranger territory, emerging from inflation theory and the landscape of possible physical laws. Here, our entire observable universe, with its hundreds of billions of galaxies, becomes just one bubble in an infinite cosmic foam. These bubble universes form when eternal inflation creates pockets where inflation ends and normal physics begins. But here's the crucial difference from level I. Each bubble universe can have different physical constants and even different physical laws. The strength of gravity, the masses of particles, the number of spatial dimensions, all these fundamental parameters might vary from bubble to bubble. Most of these universes would be sterile, unable to form atoms, molecules, or any complex structures. But among the infinite collection of bubbles, some would have physics remarkably similar to ours. The Level 2 multiverse emerges naturally from string theory, which suggests that the extra dimensions beyond our familiar 3 dimensions of space can be curled up in many different ways. Each way of compactifying these extra dimensions produces a different set of physical laws in the resulting 4-dimensional universe. The string theory landscape contains an estimated 10 circumflex, 500 different possible vacua, different ways the universe could be configured at the deepest level. This vast landscape provides a natural explanation for the fine-tuning we observe in our universe. The constants of nature appear precisely calibrated to allow for the existence of atoms, stars, galaxies, and life. In a single universe, this would be a miraculous coincidence. But in the Level 2 multiverse, we naturally find ourselves in one of the rare bubbles where physics allows for complex structures like ourselves to exist. Level 3, the quantum multiverse. Level 3 returns us to the many worlds interpretation we explored earlier, but now we can see how it fits into Tegmark's broader classification. This is the multiverse of quantum mechanics, where every quantum event causes reality to branch into multiple parallel worlds. Unlike levels I and II, which involve distant regions of space, Level 3 universes exist in the same space as ours, but in different quantum branches. The mathematics of quantum mechanics describes all possible outcomes of every quantum event as existing simultaneously in different branches of the universal wave function. When you flip a quantum coin, both heads and tails occur just in different branches of reality. The Level 3 multiverse contains every possible history that quantum mechanics allows, from the subatomic scale to the cosmic. What makes Level 3 particularly elegant is that it requires no new physics beyond what we already know. The many worlds interpretation emerges naturally from taking the Schrödinger equation seriously without adding extra assumptions about wave function collapse. Every quantum interaction you've ever experienced has created new branches of reality, each containing a different version of you, experiencing a different outcome. Level 4, the mathematical multiverse. At the summit of Tegmark's taxonomy lies Level 4, the most abstract and all-encompassing multiverse of all. Here, Tegmark proposes that every mathematically consistent structure exists as a physical reality. Our universe, with its particular set of physical laws and mathematical relationships, is just one mathematical structure among infinitely many. This mathematical universe hypothesis suggests that the distinction between mathematics and physics is artificial. We typically think of mathematics as describing physical reality, but Tegmark argues that mathematics is physical reality. Every possible equation, every geometric structure, every logical system that can exist without contradiction corresponds to an actual universe populated by conscious beings for whom those mathematical relationships constitute the laws of physics. The Level 4 multiverse contains universes with different numbers of dimensions, different types of time, different logical structures entirely. Some might be based on geometries we can barely imagine. Others might operate according to mathematical principles we haven't yet discovered. The only requirement is mathematical consistency. If a structure can be described without contradiction, then according to Level 4, it exists. This perspective places our universe in context as one particular mathematical structure capable of supporting observers complex enough to contemplate their own existence. We find ourselves in this structure not because it's special in any objective sense, but because it's one of the structures that can contain beings capable of asking why they exist. Each level of Tegmark's multiverse builds upon and encompasses the previous levels. Level I is contained within Level 2, which is contained within Level 3, which is contained within Level 4. Together they form a nested hierarchy of reality that encompasses every possible form of existence that could ever be imagined, and infinitely many that couldn't. As we breathe deeply and contemplate these expanding circles of possibility, we begin to sense our place in this vast hierarchy of being. We are expressions of mathematical possibility, conscious observers, embedded in one particular level of an infinite tower of realities, each level more vast and strange than the last. The cosmos reveals itself not as a single universe, but as an infinite symphony of mathematical structures, each playing its own unique variation on the theme of existence. In the delicate balance of cosmic forces that allowed you to exist, we discover one of the most profound mysteries in all of science. The universe appears to be exquisitely fine-tuned for the existence of life, with fundamental constants calibrated to such precise values that even tiny changes would render existence impossible. This cosmic Goldilocks problem, everything being just right for life, has puzzled scientists for decades and provides one of the strongest motivations for believing in the multiverse. Consider the strength of gravity, perhaps the most familiar fundamental force. In our universe, gravity is precisely weak enough to allow stars to burn steadily for billions of years, providing stable energy sources for planetary systems. If gravity were just slightly stronger, say, 1 trillion times stronger than the weak nuclear force, instead of 10 circumflex, 39 times stronger stars would burn through their fuel in mere thousands of years instead of billions. Complex chemistry would never have time to develop, life would be impossible, and no observers would exist to notice the problem. But gravity could also be too weak. If it were significantly weaker than it is, matter would never clump together into stars and galaxies. The universe would remain a thin, cold gas, expanding forever, with no nuclear furnaces to forge the heavy elements necessary for chemistry and life. The range of gravitational strengths compatible with a life-bearing universe is vanishingly small compared to the range of mathematically possible values. This fine-tuning extends to dozens of other physical constants. The mass of the electron determines the size of atoms and the nature of chemical bonding. If electrons were much heavier, atoms would be too small for complex chemistry. If they were much lighter, atoms would be too large and unstable. The strong nuclear force that holds atomic nuclei together is calibrated within a narrow range that allows both hydrogen and heavier elements to exist. Stronger, and all hydrogen would have fused into heavier elements in the Big Bang, leaving no fuel for stars. Weaker, and no elements heavier than hydrogen could form. Perhaps most remarkably, the cosmological constant, the energy density of empty space itself, appears to be fine-tuned to an almost incomprehensible degree. This mysterious dark energy, discovered in the 1990s to be causing the expansion of the universe to accelerate, has a value that's smaller than theoretical predictions by a factor of 10 circumflex 120. If it were much larger, space would expand so rapidly that galaxies could never form. If it were much smaller but negative, the universe would collapse before stars could ignite. The anthropic principle, first articulated by physicists Brandon Carter and John Barrow in the 1970s, provides a framework for thinking about this apparent fine-tuning. The weak anthropic principle simply observes that we must find ourselves in a universe compatible with our existence. Otherwise, we wouldn't be here to observe it. This seems obvious but has profound implications. We shouldn't be surprised to find ourselves in a life-friendly universe, because universes without observers have no one to notice their existence. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop within it. This stronger version verges on teleological thinking, the idea that the universe was designed or intended to produce life. Most scientists are uncomfortable with this interpretation because it seems to require some form of cosmic purpose or design. The multiverse provides an elegant resolution to the fine-tuning problem without invoking design or purpose. In an ensemble of universes with randomly varying physical constants, most would be sterile and lifeless. But among the vast number of possible universes, some would by chance have the right combination of parameters to support complex chemistry and life. We naturally find ourselves in one of these rare, life-friendly universes simply because we couldn't exist in any of the others. This statistical explanation becomes even more compelling when we consider specific examples of apparent fine-tuning. The resonance discovered by Fred Hoyle in the 1950s provides a beautiful illustration. Hoyle realized that for carbon to be produced in sufficient quantities in stellar cores, the carbon nucleus must have an energy level positioned at exactly the right value to allow efficient nuclear reactions. Without this precise resonance, carbon production would be suppressed, complex chemistry would be impossible, and life as we know it couldn't exist. Hoyle was so struck by this apparent coincidence that he famously declared, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics." But in the multiverse framework, this remarkable coincidence becomes an inevitable selection effect. Among the vast ensemble of possible universes with different nuclear physics, we observe ourselves in one of the few where carbon production is efficient simply because we're made of carbon. The fine-tuning observation extends beyond just the physical constants to the initial conditions of the universe itself. The Big Bang appears to have begun with an almost perfectly uniform distribution of matter and energy, with tiny fluctuations of precisely the right amplitude to grow into galaxies and stars. Too uniform, and no structure would form. Too lumpy, and matter would collapse into black holes before stars could ignite. The observed amplitude of these primordial fluctuations falls within the narrow range necessary for structure formation. Even the number of spatial dimensions appears to be fine-tuned. In universes with more than 3 spatial dimensions, planetary orbits become unstable, and atoms cannot exist in their familiar form. With fewer than 3 dimensions, complex neural networks like brains become impossible. 3 dimensions appears to be the minimum number necessary for complex information processing, while higher dimensions introduce instabilities that prevent stable structures. Recent advances in string theory have revealed an even more detailed landscape of possible universes, each with different compactifications of extra dimensions leading to different physical laws. The string landscape contains an estimated 10 circumflex 500 different vacuum states, each corresponding to a universe with different physics. Most of these would be incompatible with any form of complexity, but scattered throughout this vast landscape are rare valleys where physics allows for atoms, molecules, stars, planets, and life. As we contemplate these delicate cosmic calibrations that allow our existence, we might feel a sense of privileged specialness, as if the universe were designed specifically for us. But the multiverse suggests a different perspective. We are expressions of the universe's vast creativity, examples of what becomes possible when infinite experimentation with physical laws occasionally produces the right conditions for complexity and consciousness to emerge. We are not the purpose of the universe, but we are among its most remarkable achievements, conscious patterns that arose from the interplay of precisely calibrated forces, now capable of contemplating the very fine-tuning that made our existence possible. In the blink of an eye, literally faster than you could blink, faster than light, could travel across a proton, our entire observable universe expanded from a region smaller than a subatomic particle to the size of a grapefruit. This is the story of cosmic inflation, perhaps the most dramatic event in the history of existence, and the key to understanding how our universe became one bubble in an infinite multiverse of possibilities. The story begins in the early 1980s with a young physicist named Alan Guth, working late nights at Stanford University, struggling with one of cosmology's most perplexing problems. The universe appeared to be far too uniform. When we observe the cosmic microwave background radiation, the afterglow of the Big Bang, we see that the temperature is nearly identical in all directions, varying by only tiny fractions of a degree. This uniformity was mysterious because, according to standard Big Bang theory, widely separated regions of the early universe could never have been in contact with each other. How could they have the same temperature if they had never exchanged information? Guth's breakthrough came when he realized that this problem could be solved if the universe underwent a period of exponential expansion in its earliest moments. During this inflationary epoch, a tiny patch of space much smaller than a proton expanded so rapidly that it became larger than our entire observable universe today. Regions that are now separated by billions of light years were once close enough to exchange information and reach thermal equilibrium before inflation stretched them apart. The mathematics of inflation are breathtaking in their simplicity. The expansion is driven by a quantum field called the inflaton, trapped in a high-energy state like a ball balanced on top of a hill. While the field remains in this unstable state, it creates a repulsive gravitational effect that causes space itself to expand exponentially. The universe doubles in size every tiny fraction of a second, then doubles again and again and again in a runaway process that stretches space faster than the speed of light. But here's where the story becomes truly extraordinary. The same quantum fluctuations that created the temperature variations we observe in the cosmic microwave background also affected the inflaton field itself. In some regions, quantum fluctuations caused the field to decay quickly, ending inflation and creating normal matter and energy. In other regions, inflation continued, driving further exponential expansion. This realization, developed by physicists like Andrei Linde at Stanford and Alexander Vilenkin at Tufts University, led to the concept of eternal inflation. Once inflation begins, it never completely stops. While some regions exit inflation and become universes like ours, other regions continue inflating, creating new space that can then spawn more regions where inflation ends. The process is self-perpetuating, creating an infinite tree of bubble universes separated by vast regions of eternally inflating space. Picture a pot of boiling water with bubbles constantly forming and rising to the surface. Each bubble represents a universe like ours, while the surrounding water represents the eternally inflating space between universes. But unlike bubbles in water, these cosmic bubbles can never touch each other. They're separated by regions of space that continue expanding exponentially, creating ever more volume for new bubbles to form. The beauty of eternal inflation lies in its inevitability. Once you accept that inflation can happen at all, and we have strong evidence that it happened in our universe, the quantum nature of the inflaton field virtually guarantees that it will happen again and again in an endless cascade. Each bubble universe that forms during eternal inflation becomes a complete cosmos, potentially containing billions of galaxies and trillions of stars. Even more remarkably, different bubble universes can have different physical laws. During the inflationary process, the way extra dimensions curl up and the values of fundamental constants can vary from bubble to bubble. Some universes might have stronger gravity, others weaker electromagnetic forces. Some might have different numbers of spatial dimensions, or even different types of time. The vast majority would be sterile and lifeless, but scattered throughout the ensemble would be rare bubbles like ours, where physics allows for complexity and life. Linde's chaotic inflation model pushes this idea even further. In chaotic inflation, the inflaton field has a random distribution of values throughout space, with inflation beginning wherever the field exceeds a critical threshold. This creates a fractal structure of universes within universes, each undergoing its own period of inflation and spawning its own collection of bubble universes. The process has no beginning and no end, it simply is, generating infinite diversity across infinite space and time. The observational evidence for inflation has grown steadily stronger over the past 4 decades. The uniformity of the cosmic microwave background, the flatness of space, the spectrum of density fluctuations that seeded galaxy formation, all these observations match the precise predictions of inflationary theory. Recent measurements by the Planck satellite have confirmed inflation's predictions with remarkable accuracy, leaving little doubt that our universe underwent this period of exponential expansion. But eternal inflation makes predictions beyond what we can directly observe. The theory suggests that somewhere among the infinite collection of bubble universes, every possible outcome allowed by quantum mechanics has been realized. There are universes where slightly different laws of physics led to different evolutionary pathways, different configurations of matter and energy, different possibilities for life and consciousness. Some of these parallel universes might be nearly identical to ours, differing only in small quantum fluctuations that occurred during their inflationary epochs. Others might be radically different, with physics so alien that we can barely imagine the forms of complexity they might contain. The ensemble includes not just every universe that has formed, but every universe that could ever form under any possible variation of the inflationary process. As we contemplate this vast cosmic landscape of infinite bubble universes, we begin to understand our place in the eternal dance of creation. Our universe, with its particular combination of physical laws and initial conditions, represents just one note in an infinite symphony of cosmic evolution. Inflation didn't just create our cosmos, it created the framework for infinite cosmic creativity, ensuring that every possible variation on the theme of existence would eventually be explored somewhere in the ever-expanding multiverse. The bubbles continue forming, each one a complete world unto itself, each one adding its voice to the eternal cosmic chorus. Imagine reality as a vast cosmic symphony, but instead of instruments made of wood and metal, the fundamental strings of existence vibrate in dimensions we cannot see, creating all the particles and forces that make up our world. This is the vision of string theory, perhaps the most ambitious attempt in the history of physics to understand the deepest nature of reality. In its mathematical landscapes of hidden dimensions, we discover not just a theory of everything, but a framework for infinite universes with radically different physics. The story of string theory begins in the late 1960s with an Italian physicist named Gabriele Veneziano, who was trying to understand the strong nuclear force that holds atomic nuclei together. Veneziano discovered that certain mathematical equations describing vibrating strings could explain the behavior of particles called hadrons. What started as a modest attempt to understand nuclear physics gradually evolved into something far more ambitious, a theory that describes all fundamental particles as different vibrational modes of infinitesimally small strings. In string theory, the familiar particles of the standard model electrons, quarks, photons are not point-like objects, but tiny loops of vibrating string, smaller than anything we could ever hope to detect directly. Just as a violin string can vibrate in different modes to produce different musical notes, these fundamental strings vibrate in different patterns to create different particles. An electron is one vibrational mode, a photon another, a quark yet another. All the diversity of matter and energy emerges from the simple concept of vibrating strings. But for the mathematics of string theory to work consistently, these strings cannot vibrate in our familiar 3 dimensions of space, plus 1 of time. They require additional spatial dimensions, 6 extra dimensions in the most common formulations, for a total of 9 spatial dimensions, plus time. This might seem like a fatal flaw, since we clearly live in a world with only 3 spatial dimensions. How can a theory requiring extra dimensions possibly describe our reality? The answer lies in the concept of compactification, developed by physicists like Edward Witten and others in the 1980s. These extra dimensions are indeed present at every point in space, but they're curled up so tightly that we can't perceive them directly. Imagine looking at a garden hose from far away. It appears to be a one-dimensional line, but up close, you can see that it has additional circular dimensions wrapped around its length. Similarly, what we perceive as 3-dimensional space might actually be 9-dimensional, with 6 dimensions compactified into structures too small for us to detect. The remarkable discovery that changed everything came when string theorists realized that there are many different ways these extra dimensions can be compactified. The mathematical spaces that describe these compactifications are called Calabi-Yau manifolds after mathematicians Eugenio Calabi and Xing-Tung Yau. Each different Calabi-Yau manifold corresponds to a different way of curling up the extra dimensions, and each one produces a universe with different physical laws. The number of possible compactifications is staggering. Current estimates suggest there are roughly 10 circumflex, 500 different ways to compactify the extra dimensions of string theory. Each of these corresponds to a different vacuum state, a different ground state of the string theory landscape. In one compactification, electrons might be much heavier than in our universe. In another, gravity might be much stronger. In yet another, there might be different types of particles entirely, following different interaction rules. This vast landscape of possibilities provides a natural framework for the multiverse. If eternal inflation creates infinite bubble universes, and if string theory correctly describes the fundamental nature of reality, then different bubbles might have different compactifications of the extra dimensions. The majority of these universes would be sterile and lifeless, but scattered throughout the string landscape would be rare pockets, where the physics allows for atoms, molecules, chemistry, and life. The landscape becomes even richer when we consider brane world scenarios, another branch of string theory developed in the 1990s. In these models, our entire universe, all the matter and energy we can observe, is confined to a four-dimensional surface called a brane, floating in a higher dimensional space called the bulk. Other branes might exist in the same bulk space, carrying their own universes with their own physical laws. These parallel branes might occasionally collide, creating Big Bang-like events that give birth to new universes. Neil Turok, Paul Steinhardt, and others have developed cyclic cosmological models, where our universe undergoes repeated cycles of expansion and contraction, driven by collisions between branes. Each collision resets the cosmic clock, creating a new universe with potentially different physical constants and laws. The mathematical structure of string theory reveals connections between apparently different physical theories. What appears to be one type of string theory in one mathematical description turns out to be equivalent to a completely different theory when viewed from another perspective. These dualities suggest that the landscape of string theory might be even richer than previously imagined, with the same physical reality capable of being described by multiple, seemingly distinct, mathematical frameworks. Recent developments in holographic duality have revealed that string theories in higher dimensional spaces can be equivalent to quantum field theories on their lower dimensional boundaries. This suggests that our four-dimensional universe might actually be a holographic projection from physics occurring on a distant boundary in higher dimensional space. If true, this would mean that the fundamental description of reality requires these extra dimensions, even if we experience only a lower dimensional shadow of the full theory. The experimental challenges of testing string theory are formidable. The strings themselves are far too small to observe directly, and the extra dimensions are compactified on scales accessible only to energies far beyond any conceivable particle accelerator. But string theory makes indirect predictions that might be testable. The theory requires certain types of particles called supersymmetric partners, predicts specific patterns of cosmic strings that might be observable, and suggests signatures of extra dimensions that might appear in high-energy experiments. As we rest in contemplation of these hidden dimensions permeating every point of space around us, we begin to appreciate the vast richness that might lie just beyond our perception. The three-dimensional world we experience might be just the tip of an iceberg of reality, with vast, hidden structures determining the fundamental nature of existence. In every cubic centimeter of empty space, 6 additional dimensions curl and twist in patterns that determine why electrons have the mass they do, why gravity is as weak as it is, and why the universe has the particular combination of physical laws that allow complexity and consciousness to exist. We are three-dimensional beings living on the surface of a 9-dimensional reality, like characters in a novel, becoming aware of the vast library that contains all possible stories. In a darkened laboratory, a simple apparatus holds the key to understanding the deepest mystery of existence. 2 parallel slits cut into an opaque barrier a source of particles or light, and a detector screen. This humble setup has revealed secrets about reality that challenge our most basic assumptions about the nature of existence itself. Tonight, we'll discover how this elegant experiment opens doorways between worlds and reveals the quantum architecture underlying the multiverse. The story begins in 1801 with Thomas Young, an English physician and polymath who was investigating the nature of light. Young's original experiment used sunlight passing through two narrow slits to create an interference pattern on a distant screen, alternating bands of bright and dark that could only be explained if light behaved as a wave. When waves from the two slits arrive at the same point on the screen, they can interfere constructively to create bright regions, or destructively to create dark regions. This wave interference proved that light was not simply a stream of particles, as Newton had proposed, but possessed wave-like properties. For over a century, this seemed to settle the matter. Light was a wave, vibrating in electromagnetic fields that propagated through space. But in the early 1900s, experiments by Max Planck and Albert Einstein revealed that light also behaved like particles in certain situations, carrying discrete packets of energy called photons. This wave-particle duality became one of the central mysteries of the emerging quantum theory. The true strangeness of the double-slit experiment only became apparent when technology advanced enough to send individual particles through the apparatus one at a time. In these single particle experiments, performed first with photons and later with electrons, neutrons, and even large molecules, something remarkable occurs. Even when only one particle travels through the apparatus at a time, the familiar interference pattern gradually builds up on the detector screen as more and more particles arrive. This result defies classical intuition. How can a single particle interfere with itself? If the particle goes through one slit or the other, how does it know about the existence of the second slit to create an interference pattern? The quantum mechanical answer is that the particle doesn't go through one slit or the other. It goes through both slits simultaneously, existing in a superposition of all possible paths until it's detected at the screen. But here's where the mystery deepens. If we modify the experiment to determine which slit each particle actually passes through by placing detectors at the slits themselves, the interference pattern disappears. The particles begin behaving like classical objects, each going through one slit or the other, creating two distinct bands on the screen instead of the wave-like interference pattern. The very act of observing which path the particle takes seems to fundamentally change its behavior. This which path information creates one of the most profound puzzles in quantum mechanics. How does the particle know whether we're watching it? What constitutes an observation or measurement? Why should the presence of a detector at the slits change what happens at the distant screen? These questions have puzzled physicists for decades and led to various interpretations of quantum mechanics. The Copenhagen interpretation suggests that the act of measurement causes the quantum wave function to collapse, forcing the particle to choose a definite path. Before measurement, the particle exists in a superposition of going through both slits. During measurement, this superposition collapses into a definite state where the particle has gone through one slit or the other. But the many worlds interpretation offers a radically different explanation. In this view, the particle doesn't collapse into going through one slit or the other. Instead, reality branches into multiple parallel worlds. In some worlds, the particle goes through the left slit. In others, it goes through the right slit. The interference pattern emerges from quantum interference between these different worlds, each contributing to the final probability distribution on the screen. When we add which path detectors, we don't cause collapse, we cause the different branches of reality to become distinguishable and lose their ability to interfere with each other. The detector becomes entangled with the particle, creating distinct worlds where the detector registers different outcomes. These worlds can no longer interfere quantum mechanically because they've become isolated from each other through the process of decoherence. The delayed choice experiment, devised by John Wheeler in the 1970s, pushes this mystery even further. In this version, we can decide whether to measure which path information or allow interference after the particle has already passed through the slits, but before it reaches the screen. Remarkably, our choice of measurement in the present seems to retroactively determine the particle's behavior in the past. If we choose to measure which path, the particle appears to have gone through one slit or the other. If we choose to observe interference, the particle appears to have gone through both slits. This suggests that the notion of a particle having definite properties independent of observation might be fundamentally wrong. The act of measurement doesn't just reveal pre-existing properties, it participates in creating the reality we observe. In the many worlds framework, our choice of measurement determines which aspect of the multiverse we become entangled with, which branch of reality we experience. Recent variations of the double-slit experiment have revealed even deeper mysteries. The quantum eraser experiment shows that we can restore interference patterns even after which path information has been recorded, provided we erase that information before making our final observation. This suggests that the boundary between quantum and classical behavior is more fluid than previously thought. Experiments with large molecules like C70 fullerenes, SOCA, ball-shaped carbon molecules containing 70 atoms have demonstrated that wave-particle duality and superposition aren't limited to microscopic particles. Even these relatively large objects, containing hundreds of atoms, can pass through both slits simultaneously and create interference patterns. This pushes the boundary between quantum and classical worlds toward larger and larger objects. The double-slit experiment continues to yield new insights as technology advances. Recent experiments have demonstrated interference effects with molecules containing over 2,000 atoms, with photons traveling over cosmic distances, and with quantum states that exist for macroscopic periods of time. Each new variation reveals more about the fundamental nature of reality and the role of observation in determining what we experience. As we contemplate this simple yet profound experiment, we begin to see how it opens windows into the multiverse itself. Every particle passing through the slits potentially creates new branches of reality, new worlds where different outcomes occur. The interference pattern we observe is a ghostly signature of all these parallel worlds, a faint echo of the vast quantum symphony playing out across infinite realities. We are not separate from this process, we are part of it, quantum observers whose very act of observation participates in the creation of the reality we experience. In the quantum realm, separation is an illusion. Two particles can become so intimately connected that measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and Claude spent years trying to prove it impossible. Yet today we know that quantum entanglement is not only real, but forms the foundation for understanding how information flows between parallel realities in the multiverse. The phenomenon first emerged from the mathematical formalism of quantum mechanics in the 1930s, when Einstein, Boris Podolsky, and Nathan Rosen published their famous EPR paradox. They imagined two particles created in such a way that their quantum properties are correlated. If one has spin up, the other must have spin down. According to quantum mechanics, before measurement, each particle exists in a superposition of both spin states. But the instant we measure one particle and find it spinning up, we immediately know the other must be spinning down, even if it's on the other side of the galaxy. Einstein found this deeply troubling. How could measuring one particle instantly determine the properties of another particle far away? This seemed to violate the principle of locality, the idea that objects are only directly influenced by their immediate surroundings. Einstein argued that the particles must have definite properties all along, hidden from our view until measurement reveals them. He believed quantum mechanics was incomplete, missing some deeper layer of reality that would restore classical intuition. For 3 decades, this remained a philosophical debate, with no clear way to test who was right. Then, in 1964, an Irish physicist named John Bell proved that Einstein's hidden variable theories would produce different statistical predictions than quantum mechanics. Bell's theorem showed that any local realistic theory, one where particles have definite properties and influences, travel no faster than light, must satisfy certain mathematical inequalities. Quantum mechanics predicts these inequalities can be violated. The experimental test came in the 1980s through the elegant work of Alain Aspect and his colleagues in France. Using pairs of entangled photons, they measured correlations that clearly violated Bell's inequalities, confirming the quantum mechanical predictions and ruling out local hidden variable theories. The universe really does exhibit the spooky action at a distance that Einstein found so disturbing. But entanglement becomes even more mysterious when viewed through the lens of the many worlds interpretation. In this framework, when we measure one particle of an entangled pair, we don't cause the other particle to instantly snap into the opposite state. Instead, reality branches into multiple worlds. In some worlds, we measure spin up, and the distant particle is spin down. In other worlds, we measure spin down, and the distant particle is spin up. The correlations emerge not from instantaneous influences, but from the way reality splits consistently across different locations. This suggests that entanglement might be a window into the structure of the multiverse itself. When two particles become entangled, they form connections that persist across different branches of reality. Information about the quantum state is shared between worlds in ways that transcend our usual notions of space and time. The entangled particles aren't communicating faster than light. They're participating in a quantum symphony that plays out simultaneously across multiple realities. Recent experiments have pushed entanglement to new extremes. Scientists have created entangled states involving hundreds of photons, demonstrated entanglement between particles separated by hundreds of kilometers, and even achieved entanglement between the quantum states of tiny diamonds visible to the naked eye. Each experiment reveals more about the non-local structure of quantum reality and its implications for the multiverse. The phenomenon of quantum teleportation, first proposed in the 1990s and now routinely performed in laboratories worldwide, provides another glimpse into how information might flow between realities. In quantum teleportation, the complete quantum state of one particle can be transferred to another particle, even if they're far apart. The original particle's state is destroyed in the process, but an exact copy appears at the distant location. Crucially, this process requires a pre-existing entangled pair and cannot be used to send classical information faster than light. From a many worlds perspective, quantum teleportation demonstrates how quantum information is preserved across the branching structure of reality. When Alice measures her particle to teleport its state to Bob, reality branches into multiple worlds corresponding to different measurement outcomes. In each branch, Bob's particle acquires the appropriate quantum state to maintain the global conservation of quantum information. The process reveals how information flows through the quantum substrate that underlies all possible realities. Entanglement also plays a crucial role in the phenomenon of quantum decoherence, which explains how classical reality emerges from quantum possibility. When a quantum system becomes entangled with its environment, the different branches of its wave function rapidly become isolated from each other. They still exist in the many worlds framework, but they can no longer interfere quantum mechanically. Decoherence doesn't eliminate the other branches, it makes them effectively independent realities. This process suggests that our classical world emerges from a vast network of quantum entanglements between every particle and its environment. The chair you're sitting on appears solid and definite, not because it has collapsed into a classical state, but because it's so thoroughly entangled with the surrounding air molecules, photons, and other particles that its different quantum possibilities have become isolated into separate branches of reality. Some theorists have proposed that consciousness itself might be fundamentally connected to quantum entanglement. If our brains can maintain quantum coherence on sufficiently large scales, our conscious experience might directly participate in the branching structure of reality. We might not just observe the multiverse, we might be active participants in its creation, with our conscious choices determining which branches of reality we experience. The emerging field of quantum information theory has revealed that entanglement is more than just a curious feature of quantum mechanics. It's a fundamental resource that can be harvested and used for computation and communication. Quantum computers exploit entanglement to process information in ways that are impossible for classical computers, potentially accessing the computational power of parallel universes to solve certain problems exponentially faster. As we contemplate the invisible threads of entanglement connecting every quantum particle across space and time, we begin to appreciate the deep interconnectedness of existence. In the many worlds multiverse, we are not isolated beings, observing a distant reality. We are embedded in a vast web of quantum correlations that spans multiple realities, each choice and measurement we make rippling through the structure of existence itself. The boundaries between self and world, between here and there, between past and future, begin to dissolve in the face of quantum entanglement's profound implications. At the boundary between mind and matter lies one of the deepest mysteries in all of science: the role of consciousness in determining the nature of reality itself. When quantum physicists speak of measurement and observation, they're describing something far more profound than simply looking at a system. They're touching on questions that bridge physics and philosophy, matter and mind, the objective and subjective aspects of existence. The mystery begins with the quantum measurement problem. Before measurement, quantum systems exist in superpositions of multiple states simultaneously. An electron can be spinning both up and down, a photon can be traveling through multiple paths, a radioactive atom can be both decayed and not decayed. But the moment we perform a measurement, we always find the system in one definite state. The measurement process seems to force nature to make a choice, but the mathematics of quantum mechanics doesn't explain how or when this choice occurs. In the 1930s, mathematician John von Neumann proposed that consciousness plays a fundamental role in this process. According to the von Neumann-Wigner interpretation, the quantum wave function continues evolving in superposition until it encounters a conscious observer. At that moment, the observer's consciousness causes the wave function to collapse into a definite state. This would make consciousness a fundamental feature of physics, not just an emergent property of complex matter. The idea seems absurd at first. How could human consciousness, which evolved relatively recently in cosmic history, play such a fundamental role in the basic laws of physics? Yet, the mathematics of quantum mechanics offers no clear boundary between quantum and classical behavior. Von Neumann showed that if we describe measurement apparatus quantum mechanically, they too must exist in superposition until observed by consciousness. Consider the classic thought experiment. A quantum particle triggers a detector, which amplifies the signal through various electronic components, which ultimately displays a result on a computer screen. If we apply quantum mechanics consistently to the entire chain, the particle, detector, electronics, and even the computer screen must all exist in superposition until a conscious observer looks at the display. This suggests that consciousness might indeed play a special role in determining when superposition ends and definite reality begins. But what constitutes consciousness for the purposes of quantum measurement? Does it require human-level awareness, or would simpler forms of information processing suffice? Some interpretations suggest that even bacteria or simple devices capable of irreversibly recording information might serve as observers in the quantum mechanical sense. Others maintain that only complex, integrated systems capable of subjective experience can collapse wave functions. Giulio Tononi's integrated information theory provides a mathematical framework for thinking about consciousness and its possible role in quantum measurement. According to IIT, consciousness corresponds to integrated information by amount of information generated by a system above and beyond its parts. Systems with high integrated information, like human brains, possess rich, conscious experiences. Those with low integrated information, like simple computers, might be minimally conscious or not conscious at all. If consciousness is indeed necessary for wave function collapse, this would have profound implications for the multiverse. In the many worlds interpretation, consciousness doesn't cause collapse. Instead, it participates in the branching process. When a conscious observer encounters a quantum superposition, their consciousness itself splits along with the rest of reality. Each branch contains a version of the observer who experiences one particular outcome, but all branches are equally real. This leads to the remarkable possibility that consciousness might be the mechanism by which the multiverse explores its own possibilities. Every conscious choice, every moment of awareness, every decision, large or small, might create new branches of reality. We wouldn't just be passive observers of the multiverse. We'd be active participants in its creation, co-authors of the cosmic story unfolding across infinite realities. The split brain studies, conducted by Roger Sperry and others in the 1960s and 1970s, provide intriguing hints about the relationship between consciousness and quantum mechanics. Patients who had their corpus callosum severed to treat severe epilepsy effectively had two separate conscious systems in their brains, each controlling different aspects of behavior and experience. If consciousness plays a role in quantum measurement, what happens when a single brain contains multiple conscious observers? Stuart Hameroff and Roger Penrose have proposed that consciousness emerges from quantum processes in microtubules within brain cells. Their orchestrated objective reduction theory suggests that quantum superpositions in neural microtubules collapse in a coordinated fashion, giving rise to conscious moments. If true, this would make consciousness a fundamentally quantum phenomenon, directly connected to the measurement process that shapes reality. Recent experiments have begun exploring whether quantum effects might indeed play a role in biological systems and consciousness. Quantum coherence has been discovered in photosynthesis, bird navigation, and possibly even in neural processes. While these discoveries don't prove that consciousness causes wave function collapse, they suggest that quantum effects might be more important in biological systems than previously thought. The delayed choice quantum eraser experiments raise even deeper questions about consciousness and time. In these experiments, we can decide whether to measure which path information or observe interference patterns after a particle has already been detected. But before we look at the results, our conscious choice in the present seems to retroactively determine what kind of measurement occurred in the past. This suggests that consciousness might not just participate in creating reality, but might influence the nature of past events. Some interpretations of quantum mechanics go even further, suggesting that consciousness is fundamental to the universe itself. In these panpsychist theories, all matter possesses some form of primitive consciousness or experience. Complex systems like brains represent concentrations and integrations of this fundamental consciousness, but even electrons and photons might have rudimentary subjective experiences. The relationship between consciousness and quantum mechanics remains one of the deepest unsolved problems in science. We don't yet know whether consciousness plays a special role in quantum measurement, whether it emerges from quantum processes in the brain, or whether it's simply an emergent property of complex classical computation. But the questions themselves reveal something profound about our place in the cosmos. As we contemplate our own consciousness, contemplating consciousness, we touch on one of the great recursive mysteries of existence. We are patterns of matter and energy that have become aware of themselves, quantum systems capable of observing and perhaps influencing the quantum world that created us. In the vast multiverse of possibility, consciousness might be both the most remarkable emergence and the most fundamental feature, the universe's way of becoming aware of its own infinite nature. In the quantum world, barriers are mere suggestions. A particle approaching a wall it classically cannot climb finds ways to mysteriously appear on the other side, as if reality itself provides secret passages through the impossible. This phenomenon, known as quantum tunneling, not only enables the nuclear fusion that powers stars and the electronics that run our modern world, but might also provide the mechanism by which entire universes can transition between different states of existence. The story of quantum tunneling begins with the wave nature of matter. In 1924, Louis de Broglie proposed that all particles possess wave-like properties, with wavelengths inversely related to their momentum. When a particle encounters a barrier, a region where its energy is less than the potential energy required to classically pass through its quantum wave function, doesn't simply stop at the barrier's edge. Instead, the wave partially penetrates into the barrier, decreasing exponentially with distance, but never quite reaching zero. If the barrier is thin enough, a small portion of the wave function emerges on the other side. This means there's a non-zero probability of finding the particle beyond the barrier, even though it never had enough energy to classically climb over it. The particle doesn't gradually burrow through the barrier like a classical object, and it simply appears on the other side with the same energy it had before, as if the barrier had temporarily become transparent. This quantum tunneling is responsible for alpha decay in radioactive nuclei. The alpha particle, a helium nucleus inside a heavy nucleus like uranium, doesn't have enough energy to escape the nuclear potential well that binds it. Classical physics would predict that it should remain trapped forever, but quantum mechanics allows the alpha particle to tunnel through the nuclear barrier, explaining why radioactive decay occurs at all and providing the precise mathematical description of decay rates. On a cosmic scale, quantum tunneling enables the nuclear fusion reactions that power stars. The temperatures and pressures in stellar cores create conditions where hydrogen nuclei can approach each other closely, but even these extreme conditions aren't quite enough for nuclei to overcome their mutual electrical repulsion. Quantum tunneling allows some nuclei to penetrate the Coulomb barrier and fuse, releasing the energy that makes stars shine and creates the heavy elements necessary for planets and life. But quantum tunneling has implications that extend far beyond nuclear physics. In quantum field theory, the vacuum itself can tunnel between different states. Imagine the universe as existing in a false vacuum, a state that appears stable but isn't the lowest possible energy configuration. Just as a ball balanced on a hill might remain there for a long time before rolling down to a lower position, the universe might exist in a metastable state that could spontaneously tunnel to a lower energy configuration. Such a tunneling event would create a bubble of true vacuum, expanding at the speed of light, fundamentally altering the laws of physics within the bubble. The mass of electrons might change, the strength of forces might shift, the very structure of space-time itself might be transformed. Any complex structures, like atoms, molecules, stars, and life, would be destroyed as the bubble of new physics swept through space. This false vacuum decay scenario, first explored by physicists like Sidney Coleman in the 1970s, provides a mechanism for universe transitions within the multiverse framework. If our universe exists in a false vacuum, quantum tunneling could eventually cause it to decay into a different universe with different physical laws. The tunneling event wouldn't just change our universe, it would create new regions of space-time with fundamentally different properties. The mathematics of false vacuum decay are closely related to the tunneling of particles through barriers, but scaled up to cosmic proportions. The barrier in this case is the energy difference between different vacuum states, and the particle that tunnels is a field configuration spanning vast regions of space. The probability of such tunneling events depends on the height and width of the energy barriers between different vacuum states in the landscape of possible physics. String theory provides a rich framework for understanding these vacuum transitions. The string landscape contains an estimated 10 circumflex 500 different vacuum states, each corresponding to a different way of compactifying the extra dimensions, and each giving rise to different physical laws. Quantum tunneling between these vacua could allow universes to explore different regions of the landscape, creating a vast network of connected realities with different physics. Instant-on solutions to the field equations that describe tunneling between different vacuum states provide the mathematical description of these universe transitions. Like virtual particles that mediate forces in quantum field theory, instantons are mathematical constructs that enable transitions between classically disconnected regions of the landscape. They represent quantum fluctuations that temporarily connect different universes, allowing transitions that would be impossible in classical physics. The eternal inflation framework amplifies the importance of vacuum tunneling. In regions where inflation continues, quantum fluctuations can cause transitions between different vacuum states, creating bubble universes with different physics. Some bubbles might tunnel back and forth between nearby vacua, creating a complex web of interconnected universe types. Others might tunnel to completely different regions of the landscape, exploring radically different possibilities for physical law. Recent developments in quantum field theory have revealed that tunneling processes might be enhanced in curved spacetime. The expansion of the universe, quantum fluctuations in the gravitational field, and interactions with dark energy could all influence the rate at which vacuum tunneling occurs. This suggests that the cosmic environment itself plays a role in determining which universe transitions are possible and how rapidly they occur. The concept of quantum tunneling between universes raises profound questions about the nature of physical law and cosmic evolution. If the fundamental constants and forces we observe are not fixed features of reality, but rather temporary aspects of our current vacuum state, then the entire history of our universe, the formation of galaxies, the evolution of stars, the development of life and consciousness, represents just one chapter in a much larger story of cosmic exploration through the landscape of possible physics. Laboratory experiments continue to reveal new aspects of quantum tunneling, from the behavior of electrons in novel materials to the dynamics of ultra-cold atomic gases. Each discovery adds to our understanding of how quantum systems can transcend classical barriers and explore states that would otherwise be inaccessible. These insights provide the foundation for understanding how entire universes might tunnel between different configurations of reality. As we contemplate the possibility that our entire cosmos might someday tunnel into a completely different state of existence, we gain a new perspective on the temporary nature of everything we consider permanent. Why don't we see quantum superpositions in our everyday lives? Why does a cat appear to be either dead or alive, never both simultaneously? Why do classical laws emerge from quantum foundations? The answer lies in one of the most important discoveries in modern physics: decoherence, the process by which quantum possibilities become classical realities through their interaction with the environment. The mystery of the quantum to classical transition puzzled physicists for decades. Quantum mechanics describes a world of superpositions and entanglements, where particles exist in multiple states simultaneously and distant objects can be mysteriously correlated. Yet our everyday experience reveals a classical world of definite properties and local interactions. Somewhere between the quantum realm of atoms and the classical world of cats and chairs, the strange features of quantum mechanics seem to disappear. Early attempts to solve this puzzle focused on the measurement process itself. The Copenhagen interpretation suggested that measurement causes wave function collapse, forcing quantum systems to choose definite states. But this left many questions unanswered. What constitutes a measurement? When exactly does collapse occur? Why should quantum systems behave differently during observations? The breakthrough came in the 1970s and 1980s through the work of physicists like Wojciech Zurek, who realized that the key wasn't measurement, but rather the inevitable interaction between quantum systems and their environments. Every quantum system, from electrons to cats to galaxies, is constantly interacting with the world around it through photons, air molecules, gravitational fields, and countless other environmental factors. These environmental interactions don't destroy the quantum nature of reality, they redistribute it. When a quantum system in superposition interacts with its environment, the system and environment become entangled. The superposition doesn't collapse. Instead, it spreads out into the environment, becoming diluted among so many environmental degrees of freedom that it becomes effectively unobservable. Consider a dust particle floating in air, existing in a quantum superposition of being in two slightly different positions simultaneously. Classical physics would suggest this superposition should be detectable if we could make precise enough measurements. But the particle is constantly colliding with air molecules, each collision entangling its position with the motion of environmental particles. Within an incredibly short time, much less than a microsecond, the superposition becomes entangled with the positions and momenta of countless air molecules. The original superposition still exists in the mathematics of the quantum state, but it's now distributed across so many environmental particles that it's impossible to access experimentally. The dust particle appears to have a definite position, not because its wave function has collapsed, but because the quantum coherence has been diluted into the environment beyond any hope of recovery. This process of environmental entanglement explains why larger objects appear more classical than smaller ones. A single photon can maintain quantum coherence for long periods because it interacts weakly with its environment. An electron in an isolated atom can remain in superposition for milliseconds or even seconds. But a macroscopic object like a baseball is constantly bombarded by thermal photons, air molecules, and other environmental influences that rapidly destroy any quantum coherence. The timescales involved in decoherence are remarkably short for macroscopic objects. A dust particle 1 micrometer in diameter floating in air will decohere in about 10 circumflex negative 31 seconds. A baseball will decohere in approximately 10 circumflex negative 23 seconds. These times are so short that quantum superpositions of macroscopic objects are destroyed almost instantly, long before we could ever hope to detect them. But decoherence doesn't eliminate the other branches of the wave function, it simply makes them inaccessible to us. In the many worlds interpretation, all the possible outcomes of quantum events continue to exist in parallel branches of reality. Decoherence explains why these branches become independent and why we experience only one branch at a time, but it doesn't eliminate the others. This leads to a profound realization. The classical world we experience is not the fundamental level of reality, but rather an emergent approximation. The underlying quantum reality continues to exist and evolve according to the Schrödinger equation, but our classical experience emerges from our inability to access the full quantum state due to environmental entanglement. The process also explains why certain properties appear more classical than others. Position and momentum decohere rapidly through environmental interactions, which is why objects appear to have definite locations and velocities. But other quantum properties, like the spin states of well-isolated particles, can maintain coherence for much longer periods because they couple more weakly to the environment. Modern experiments have confirmed the predictions of decoherence theory in remarkable detail. Scientists can now control the rate of decoherence by carefully engineering the environment around quantum systems. In isolated systems at ultra-low temperatures, quantum coherence can be preserved for increasingly long times, allowing the observation of quantum effects in larger and larger objects. These controlled decoherence experiments have revealed that the boundary between quantum and classical behavior is not fundamental but environmental. By reducing environmental interactions, scientists have demonstrated quantum interference effects in molecules containing thousands of atoms. By increasing environmental coupling, they can watch quantum coherence disappear in real time, confirming the detailed predictions of decoherence theory. The discovery of decoherence has revolutionized our understanding of quantum mechanics and its relationship to classical physics. It shows that classical reality emerges naturally from quantum foundations without requiring mysterious collapse processes or arbitrary boundaries between quantum and classical domains. The apparent solidity and definiteness of the classical world is not evidence against quantum mechanics, but rather a natural consequence of environmental interaction. This perspective transforms our understanding of measurement itself. Measurement devices don't cause wave function collapse. They become entangled with the quantum systems they measure, spreading the superposition into the environment. The observer effect isn't about consciousness causing collapse, but about the unavoidable entanglement between measuring apparatus and measured system. Decoherence also provides insights into the arrow of time and the emergence of classical causality. The irreversible spread of quantum information into environmental degrees of freedom creates a preferred direction of time, explaining why we remember the past but not the future, and why cause typically precedes effect in our classical experience. As we contemplate the dance between quantum possibility and classical experience, we begin to understand that the solid, definite world around us is like the surface of a deep ocean, appearing calm and stable, while vast currents of quantum possibility flow beneath. At the heart of quantum mechanics lies a paradox that has puzzled physicists for nearly a century: the measurement problem. How does the quantum world of infinite possibilities transform into the classical world of definite outcomes? When exactly does this transformation occur, and what triggers it? Tonight, we explore the various solutions that different interpretations of quantum mechanics offer to this fundamental mystery, each revealing different aspects of reality's deep structure. The measurement problem emerges from the mathematical formalism of quantum mechanics itself. The Schrödinger equation describes how quantum systems evolve over time, preserving superpositions and maintaining the smooth, deterministic flow of quantum information. But when we perform measurements, we never observe superpositions directly. Instead, we always find systems in definite states, as if the smooth quantum evolution has been interrupted by something fundamentally different. John von Neumann formalized this puzzle in the 1930s by describing measurement as a chain of quantum interactions. When we measure an electron's spin, the electron interacts with a detector, which interacts with amplification circuits, which interact with a display screen, which interacts with our eyes and brain. If we apply quantum mechanics consistently to this entire chain, every component should exist in superposition until something breaks the chain and forces definite outcomes. Von Neumann identified two distinct types of evolution in quantum mechanics: the smooth, deterministic evolution described by the Schrödinger equation, process 1, and the sudden, probabilistic changes that occur during measurements, process 2. But the boundary between these processes remained mysterious. At what point in the measurement chain does process 1 give way to process 2? What physical mechanism triggers this transition? The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, sidesteps the measurement problem by declaring it a non-issue. According to this interpretation, quantum mechanics simply doesn't apply to macroscopic objects like measurement apparatus. The quantum formalism describes microscopic systems until they interact with classical measuring devices, at which point the wave function collapses and definite outcomes emerge. The boundary between quantum and classical is built into the interpretation by Fiat. But many physicists found the Copenhagen interpretation unsatisfying. Why should nature have a fundamental boundary between quantum and classical behavior? What physical principle determines where this boundary lies? The interpretation seemed to require an arbitrary division of the world into quantum systems and classical observers, with no clear criteria for making this division. The many worlds interpretation offers a radically different solution. There is no measurement problem because there is no wave function collapse. Every possible outcome of every quantum measurement actually occurs, but in different branches of reality. When we measure an electron's spin, the universe splits into branches where we observe spin up and branches where we observe spin down. The apparent randomness of quantum measurements emerges from our ignorance about which branch we'll find ourselves in. This elegant solution eliminates the need for arbitrary boundaries between quantum and classical domains. The Schrödinger equation governs all of reality, from electrons to galaxies to observers themselves. Measurement devices and human consciousness are just as quantum mechanical as the systems they observe. The illusion of wave function collapse emerges from our limited perspective, as observers embedded within one branch of the universal wave function. The GRW theory, developed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in the 1980s, takes a different approach by modifying the Schrödinger equation itself. According to GRW, quantum systems occasionally undergo spontaneous collapses, even without external measurement. These collapses occur randomly, with rates that increase rapidly with the number of particles in the system. For isolated microscopic systems, collapses are so rare that quantum coherence can persist for long periods. But for macroscopic objects containing many particles, spontaneous collapses occur frequently enough to maintain classical behavior. The GRW theory provides a complete solution to the measurement problem by making wave function collapse a fundamental physical process, rather than something that emerges from measurement interactions. The theory makes testable predictions about the rate of spontaneous collapse and suggests experiments that could distinguish it from other interpretations. However, these experiments require detecting incredibly tiny effects that remain at the edge of current technology. David Bohm's pilot wave theory offers yet another perspective on the measurement problem. In this interpretation, particles always have definite positions and velocities, guided by a quantum wave that evolves according to the Schrödinger equation. The wave function doesn't represent the probability of finding particles in different states. It represents a real physical field that guides particle motion. Measurements reveal pre-existing properties, rather than creating them through collapse. The pilot wave theory reproduces all the predictions of standard quantum mechanics, while maintaining a completely deterministic and realistic description of physical processes. The apparent randomness of quantum measurements emerges from our ignorance about the initial conditions of the quantum wave field, similar to how chaos theory explains apparent randomness in classical systems. However, the theory requires accepting faster-than-light influences between distant particles, challenging our usual notions of locality. More recent approaches to the measurement problem have focused on the role of information and thermodynamics. Cubism, quantum Bayesianism, developed by Christopher Fuchs and others, treats quantum states as degrees of belief held by individual observers rather than objective properties of physical systems. In this view, wave function collapse represents the updating of an observer's beliefs based on measurement outcomes, similar to how Bayesian statistics describes learning from new information. The consistent histories approach, pioneered by Robert Griffiths and later developed by Murray Gell-Mann and James Hartle, attempts to apply quantum mechanics to the entire universe by focusing on consistent sets of alternative histories. According to this interpretation, we can assign probabilities to different possible histories of the universe, but only if we choose a consistent family of histories that don't interfere quantum mechanically with each other. Environmental decoherence, which we explored in the previous chapter, provides crucial insights into the measurement problem without fully solving it. Decoherence explains why superpositions become unobservable due to environmental entanglement, but it doesn't explain why we observe particular outcomes rather than others. The preferred basis problem why decoherence selects certain properties, like position and energy over others, remains an active area of research. Recent experimental developments have pushed the boundaries of our understanding of the measurement problem. Scientists can now create and maintain quantum superpositions in increasingly large and complex systems, from individual atoms to molecules containing thousands of atoms to mechanical oscillators visible to the naked eye. Each advance in experimental control reveals new aspects of the quantum to classical transition. As we contemplate these various approaches to understanding, measurement, and observation, we see how different solutions lead to profoundly different pictures of reality itself. Imagine a universe almost identical to ours, where history unfolded along nearly the same path until a single quantum event, perhaps the decay of a radioactive atom in someone's brain during a crucial decision, sent reality branching in a slightly different direction. These mirror worlds, separated from us by the thinnest quantum veils, might contain versions of ourselves, living out alternative histories, exploring the roads not taken in the grand adventure of existence. The concept of mirror worlds emerges naturally from the many worlds interpretation of quantum mechanics. Every quantum event that could unfold in multiple ways does unfold in multiple ways, creating parallel branches of reality that diverge from a common quantum ancestor. Most of these branches quickly become very different from our own, but some remain eerily similar, differing only in small details that accumulate slowly over time. Consider the quantum events occurring in your brain right now. Neurons fire based on complex electrochemical processes that involve quantum tunneling across synaptic gaps. Ion channels open and close due to thermal fluctuations that are fundamentally quantum mechanical. The precise timing of neural activity depends on molecular processes that exist at the boundary between quantum and classical behavior. Each of these microscopic events could potentially unfold in slightly different ways, creating branches where your thoughts and decisions differ in subtle ways. In most cases, these quantum differences would be averaged out by the massive redundancy of neural processing. Your brain contains roughly 86 billion neurons, each connected to thousands of others through trillions of synapses. Small quantum fluctuations in individual synapses are unlikely to significantly affect the overall pattern of neural activity that constitutes your thoughts and decisions. But occasionally, a quantum event might occur at a critical moment when your brain is delicately balanced between different possible responses. Perhaps you're deciding whether to take a new job, weighing numerous factors in a mental process that could go either way. In our universe, a particular pattern of neural firing tips the balance toward accepting the position. But in a nearby branch of the multiverse, a slightly different sequence of quantum events in your synapses leads to a different pattern of neural activity, and you decide to turn down the offer. Two versions of you now live in parallel worlds, each pursuing different career paths. The butterfly effect, the idea that small changes can lead to large consequences over time, suggests that even tiny quantum differences could eventually produce dramatically different histories. In the career example, your decision to accept or reject the job offer might lead to meeting different people, living in different places, having different relationships and experiences. Over decades, the two versions of your life could become completely unrecognizable to each other. But chaos theory also reveals that some systems are more stable than others. Attractors and regions of phase space toward which systems naturally evolve can create robustness against small perturbations. Many aspects of historical development might be determined by such attractors, making certain outcomes nearly inevitable, despite quantum uncertainties. The discovery of agriculture, the development of writing, the Industrial Revolution, these major transitions might occur in most branches of history because they represent stable attractors in the space of possible civilizational development. This leads to fascinating questions about parallel evolution in mirror worlds. Would life on Earth follow similar patterns in nearby branches of the multiverse? The fundamental laws of chemistry and physics are the same, so the basic mechanisms of evolution, natural selection, genetic drift, adaptation, would operate similarly. But the specific details of evolutionary history depend on countless contingent events, from asteroid impacts to climate fluctuations to random genetic mutations. In some mirror worlds, the asteroid that killed the dinosaurs might have missed Earth entirely, leading to continued dinosaur evolution and perhaps the development of intelligent reptilian species. In others, early human ancestors might have evolved differently, leading to intelligent hominids with different physical characteristics or cognitive abilities. The possibilities are endless, constrained only by the laws of biology and the particular environmental conditions of Earth. The convergent evolution we observe in our own world, the independent development of similar features like eyes, wings, and echolocation in unrelated species, suggests that some evolutionary solutions might be particularly likely to emerge. Intelligence itself might be such a convergent solution, arising independently in multiple lineages across different branches of the multiverse. This could mean that many mirror worlds contain intelligent species, though they might be quite different from humans. Cultural evolution in mirror worlds presents even more intriguing possibilities. Human societies might develop along similar lines due to shared cognitive biases and environmental constraints, leading to recognizable patterns of social organization, technological development, and artistic expression. But cultural evolution is also highly contingent on particular historical circumstances, suggesting that most mirror worlds would contain human societies dramatically different from our own. Language evolution provides a particularly fascinating case study. All human languages share certain universal features: grammar, recursion, and the ability to express complex abstract concepts that seem to emerge from the structure of human cognition. But the specific words, sounds, and grammatical structures of particular languages are highly contingent on historical accidents. Mirror worlds might contain human societies, speaking languages utterly unlike any on Earth, yet built from the same underlying cognitive architecture. The scientific revolution itself might unfold differently in mirror worlds. Perhaps Galileo was never born, or Newton made different discoveries, or Einstein pursued a career in music instead of physics. Would different individuals make the same scientific breakthroughs? Would science develop along completely different lines? Or are certain scientific discoveries inevitable once a civilization reaches sufficient technological sophistication? Recent research in the foundations of physics suggests that even the fundamental constants of nature might vary slightly between different branches of the multiverse. In eternal inflation models, different bubble universes can have different values for parameters like the strength of gravity or the mass of the electron. Mirror worlds with slightly different physics might evolve in dramatically different ways, perhaps leading to forms of complexity and consciousness utterly unlike anything in our universe. The existence of mirror worlds raises profound questions about personal identity and the nature of the self. If there are countless versions of you living out different lives in parallel realities, which one is the real you? Are they all equally valid expressions of your potential? Do the choices you make in this reality somehow affect your parallel selves, or are they completely independent beings who happen to share your quantum origin? As we drift deeper into contemplation of these parallel possibilities, we begin to see ourselves not as singular beings, but as part of a vast ensemble of potential selves, each exploring different paths through the landscape of possibility. In the faint glow that fills the universe, the cosmic microwave background radiation, we might be seeing the first whispers of evidence for the multiverse itself. This ancient light, released when the universe first became transparent about 380,000 years after the Big Bang, carries within its subtle patterns potential signatures of collisions with other universes, violations of cosmic symmetry, and hints that our cosmos is just one bubble in an infinite sea of realities. The cosmic microwave background represents our most direct view of the early universe, a baby picture of the cosmos when it was only a tiny fraction of its current age. As the universe expanded and cooled from its initial hot, dense state, electrons and protons combined to form neutral hydrogen atoms for the first time. This recombination event released photons that had been trapped in the hot plasma, allowing light to travel freely through space for the first time. These photons have been traveling through the expanding universe ever since, cooled by cosmic expansion, from visible light to microwave radiation. When scientists first detected this background radiation in the 1960s, they expected it to be perfectly uniform, reflecting the smooth, homogeneous early universe predicted by standard Big Bang theory. But as measurement techniques improved, tiny variations began to emerge, temperature fluctuations of only a few parts in 100,000 that represent the seeds from which all cosmic structure eventually grew. These fluctuations tell a remarkable story. They are the stretched and amplified remnants of quantum fluctuations that existed in the early universe during the inflationary epoch. Inflation took microscopic quantum uncertainties and stretched them to cosmic scales, creating the slight density variations that would eventually grow into galaxies, stars, and planets. In a very real sense, we owe our existence to quantum fluctuations that occurred when the universe was smaller than a proton. But careful analysis of the cosmic microwave background has revealed puzzling features that don't match the predictions of standard cosmological models. These anomalies might be the first hints that our universe exists within a larger multiverse structure, bearing the subtle scars of its interactions with other realities. The most striking anomaly is the axis of evil, a provocative name given to an unexpected alignment in the largest scale fluctuations of the cosmic microwave background. According to inflation theory, these fluctuations should be randomly oriented with no preferred direction in space. The universe should look statistically the same in all directions, a property cosmologists call isotropy. But observations reveal that the largest temperature variations seem to be aligned with the plane of our solar system and the direction of Earth's motion through space. This alignment is deeply puzzling because there's no known reason why the cosmic microwave background should have any special relationship to our local environment. The radiation was emitted when the universe was much younger and smaller, long before our solar system existed. The fact that its largest scale patterns align with local features suggests either an incredible coincidence or some systematic effect that violates our understanding of cosmic isotropy. Another intriguing anomaly is the cold spot, a region of the cosmic microwave background that's significantly colder than the surrounding area. While random fluctuations can create hot and cold spots, this particular cold spot is larger and more pronounced than inflation theory predicts should be likely. Some cosmologists have suggested it might be the signature of a collision between our bubble universe and another universe during the early stages of cosmic evolution. The mathematics of eternal inflation predict that bubble universes should occasionally collide, creating observable signatures in the cosmic microwave background. When two expanding bubbles of space touch, the collision creates shock waves that propagate through both universes, leaving behind patterns of temperature variation that could persist to the present day. These collision signatures would appear as circular or elliptical patterns in the microwave background with specific temperature and polarization characteristics. Several research groups have searched for these collision signatures using increasingly sophisticated statistical analysis techniques. While no conclusive evidence has been found, some studies have identified circular patterns that might be consistent with bubble collisions. The challenge is distinguishing genuine collision signatures from the countless random patterns that naturally arise in any complex dataset. The Planck satellite, launched by the European Space Agency in 2009, provided the most detailed map of the cosmic microwave background ever created. Its measurements confirmed many of the anomalies seen in earlier data, while revealing new puzzles. The overall statistical properties of the fluctuations match inflation theory remarkably well, but several specific features remain unexplained by standard models. One particularly intriguing feature is the apparent suppression of fluctuations on the largest observable scales. According to inflation theory, temperature variations should have roughly the same amplitude at all scales. But observations show that the largest scale fluctuations are significantly weaker than expected. This could indicate that our observable universe is smaller than the region that underwent inflation, providing evidence that we see only a small portion of a much larger, inflated region. The hemispherical asymmetry provides another puzzle. The cosmic microwave background shows slightly more power in fluctuations in one hemisphere of the sky compared to the opposite hemisphere. This breaks the isotropy that inflation theory predicts, suggesting that our patch of the universe might have special properties or might have been influenced by structures beyond our observable horizon. Some theorists have proposed that these anomalies could be signatures of the multiverse itself. If our universe is embedded in a larger structure containing other universes, gravitational effects from nearby universes might create asymmetries in our cosmic microwave background. Alternative models suggest that we might be living in a universe with non-trivial topology, perhaps shaped like a dodecahedron or connected to itself in complex ways that would create observable patterns in the background radiation. The debate over these anomalies continues as new data and analysis techniques become available. Future observations with improved sensitivity and resolution might reveal whether these patterns are genuine signatures of new physics or subtle systematic effects that we don't yet understand. The James Webb Space Telescope and other next-generation instruments will provide new ways to probe the early universe and test multiverse predictions. As we contemplate this ancient light that has traveled billions of years to reach us, we're reminded that the cosmos itself might be trying to tell us about its deeper nature. Reality might be the ultimate magic trick, a three-dimensional experience emerging from information encoded on a two-dimensional surface, like a hologram that creates the illusion of depth from flat patterns of light and shadow. This profound possibility, known as the holographic principle, suggests that our entire universe, with all its complexity and apparent volume, might be nothing more than information painted on a distant boundary, with implications that reach deep into the nature of the multiverse itself. The story begins with one of the strangest discoveries in theoretical physics. Black holes contain the maximum amount of information that can be stored in any given region of space. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that the entropy of a black hole, a measure of how much information it contains, is proportional not to its volume, as we might expect, but to the area of its event horizon. A black hole twice as wide contains 4 times as much information, not 8 times as we would expect if information were distributed throughout its volume. This area law for entropy suggests something profound about the nature of information and space itself. If the ultimate limit on information storage depends on area rather than volume, perhaps the information describing everything inside a region of space can be encoded on its boundary. Just as a hologram stores 3-dimensional images as patterns on a 2-dimensional surface, the physics inside any volume of space might be completely determined by information encoded on its boundary. Gerard Hooft and Leonard Susskind independently developed this insight into the holographic principle in the 1990s. According to this principle, any theory of quantum gravity in a region of space should be equivalent to a quantum field theory living on the boundary of that region, but with one fewer spatial dimension. The 3-dimensional physics we experience might be a holographic projection from information processed on a 2-dimensional cosmic screen. The most concrete realization of the holographic principle came through the ADS divided by CFT correspondence, discovered by Juan Maldacena in 1997. This remarkable duality shows that string theory in a 5-dimensional anti-de Sitter space, ADS, is mathematically equivalent to a conformal field theory, CFT, living on its 4-dimensional boundary. Every process that occurs in the bulk 5-dimensional space has a corresponding description in terms of the boundary 4-dimensional theory. This isn't just a mathematical curiosity, it suggests that our familiar 3-dimensional world might be the holographic boundary description of physics occurring in a higher dimensional space. We might be living on the cosmic equivalent of a computer screen, with our 3-dimensional experience emerging from information processing on a 2-dimensional surface. Everything we perceive as volume, depth, and 3-dimensional structure could be an emergent property of boundary dynamics. The holographic principle has profound implications for understanding black holes and the information paradox. When matter falls into a black hole, what happens to the information it contains? Quantum mechanics insists that information cannot be destroyed, but general relativity suggests that anything crossing the event horizon is lost forever. The holographic principle resolves this paradox by showing that the information never really goes inside the black hole, it's always encoded on the event horizon surface, even though it appears to an outside observer that objects fall through. This resolution suggests that the interior of a black hole might not be fundamental reality, but rather an emergent description that arises from information processing on the event horizon. The falling observer experiences crossing the horizon and seeing the black hole interior, but this experience is holographically encoded in the boundary dynamics. Both descriptions are valid, but the boundary description is more fundamental. The implications extend far beyond black holes to the structure of space-time itself. If the holographic principle is correct, then space and time might not be fundamental ingredients of reality, but rather emergent properties that arise from more basic information-theoretic processes. The geometry of space-time could be a kind of error-correcting code, with the apparent 3-dimensional structure emerging from quantum entanglement patterns in the boundary theory. Recent research has explored how quantum entanglement might be the fundamental building block from which space itself emerges. When regions of the boundary theory are highly entangled, they correspond to regions of the bulk space that are closely connected. When entanglement is broken, space becomes disconnected. The familiar notion of distance and spatial separation might be emergent properties of entanglement structure rather than fundamental features of reality. This entanglement-based picture of space-time has led to new insights about wormholes, hypothetical tunnels connecting distant regions of space. In the holographic description, traversable wormholes correspond to specific types of quantum entanglement between different regions of the boundary theory. Creating a wormhole requires establishing and maintaining the right kind of quantum correlations, suggesting that space-time connectivity is fundamentally about information rather than geometry. The holographic principle also provides new perspectives on the multiverse. If our universe is holographically encoded on a boundary surface, what lies beyond that boundary? Different regions of the boundary might correspond to different universes, each with its own holographic bulk space. The multiverse could be a vast collection of holographic projections, each arising from information processing on different parts of a higher dimensional boundary. String theory's landscape of possible universes takes on new meaning in the holographic context. Each different compactification of extra dimensions corresponds to a different type of holographic duality, with different boundary theories giving rise to different bulk physics. The 10 circumflex 500 possible string vacua might represent different ways of organizing information on the cosmic boundary, each projection creating a universe with different physical laws and constants. The computational interpretation of the holographic principle suggests that reality might literally be a vast information processing system. The boundary theory performs computations whose outputs we experience as three-dimensional physics. Consciousness, matter, energy, and space-time itself might all be emergent properties of these computational processes. We could be information patterns contemplating our own informational nature. Experimental tests of the holographic principle remain challenging, but some possibilities are emerging. High-energy particle collisions might reveal signatures of extra dimensions or holographic structure. Measurements of quantum entanglement in condensed matter systems might illuminate how spatial structure emerges from entanglement patterns. Even astronomical observations might eventually reveal holographic signatures in the cosmic microwave background or other cosmological phenomena. As we contemplate the possibility that our entire reality is a holographic projection from a distant boundary, we're invited to reconsider our most basic assumptions about the nature of existence. In 1998, astronomers made a discovery that shattered our understanding of cosmic evolution. The universe's expansion is not slowing down, as everyone expected, but accelerating. This mysterious acceleration is driven by an even more mysterious component called dark energy, which comprises roughly 68% of everything that exists. But dark energy might be more than just a cosmic oddity. It could be our first direct evidence that we live in a multiverse where different universes have different vacuum energies. The story begins with two competing teams of astronomers studying Type Ia supernovae, stellar explosions, so uniform that they can serve as cosmic lighthouses, allowing precise measurements of distances across the universe. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, both expected to measure how much the universe's expansion was slowing down due to the gravitational pull of matter. What they found instead was completely unexpected. Distant supernovae appeared dimmer than they should if the universe were decelerating, indicating that they were farther away than expected. The only way to explain this observation was if the expansion of space itself was accelerating, stretching the universe at an ever-increasing rate. Something was pushing space apart with enough force to overcome the gravitational attraction of all the matter in the universe. This something was dubbed dark energy, and it immediately became the deepest mystery in cosmology. Unlike matter, which becomes diluted as the universe expands, dark energy appears to maintain constant density even as space grows. As the universe gets larger, the total amount of dark energy increases, providing more and more energy to drive accelerated expansion. The universe is dominated not by the matter and radiation we can observe, but by an invisible energy field that fills all of space. The simplest explanation for dark energy is the cosmological constant, a term that Einstein originally introduced into his equations of general relativity to allow for a static universe. This constant represents the energy density of empty space itself, what physicists call vacuum energy. Quantum field theory predicts that even empty space should contain zero-point fluctuations that contribute to vacuum energy, but the predicted value is larger than the observed dark energy density by a factor of 10 circumflex 120, the largest discrepancy between theory and observation in the history of science. This enormous discrepancy suggests that something is fine-tuning the vacuum energy to an incredibly precise value. If the cosmological constant were much larger, space would expand so rapidly that matter could never clump together to form galaxies and stars. If it were much smaller but negative, the universe would collapse before life could evolve. The observed value appears to be precisely calibrated to allow for a universe with structure and complexity. The multiverse provides an elegant solution to this fine-tuning problem. In eternal inflation models, different bubble universes can have different values for the cosmological constant, depending on the particular way that vacuum energy settles in each bubble. Most universes would have cosmological constants that make them uninhabitable, either expanding too rapidly for structure formation or collapsing too quickly for evolution. But among the infinite collection of bubble universes, some would by chance have values similar to what we observe. This anthropic explanation for dark energy represents one of the strongest motivations for believing in the multiverse. The fine-tuning of the cosmological constant is so extreme that it seems to require either divine intervention or a vast ensemble of universes with different properties. The multiverse framework transforms an inexplicable cosmic coincidence into a natural selection effect. We find ourselves in a universe with a life-friendly cosmological constant because we couldn't exist in any of the others. String theory's landscape of possible vacua provides a concrete mechanism for generating universes with different dark energy densities. Each of the 10 circumflex 500 possible compactifications of extra dimensions corresponds to a different vacuum state with its own value for the cosmological constant. Most of these vacua would produce universes with enormous positive or negative cosmological constants, but scattered throughout the landscape would be rare valleys where the vacuum energy is small enough to permit structure formation. Recent observations have begun to reveal more details about dark energy's properties and evolution. The Dark Energy Survey, the Planck satellite, and other projects have measured how dark energy's effects have changed over cosmic history. So far, the data is consistent with a simple cosmological constant that has remained constant throughout the universe's evolution. But some measurements hint at possible variations that could indicate a more complex form of dark energy. If dark energy is not a simple cosmological constant, but rather a dynamic field called quintessence, it could evolve over time and potentially vary from place to place. Different regions of the multiverse might not only have different average values for dark energy, but also different evolutionary histories. Some universes might undergo periods of acceleration, followed by deceleration, creating complex cosmological cycles that could affect the formation of structure and the development of life. The future evolution of dark energy will determine the ultimate fate of our universe. If dark energy continues to accelerate expansion at its current rate, the universe will enter a phase called the Big Rip, where acceleration becomes so extreme that it overcomes all other forces. First, galaxy clusters will be torn apart, then individual galaxies, then solar systems, then planets, and finally atoms themselves will be disrupted by the accelerating expansion of space. But in the multiverse context, even this cosmic apocalypse might not be the end of the story. Some theories suggest that the Big Rip could trigger the formation of new universes through quantum fluctuations in the rapidly expanding space. The vacuum energy that drives dark energy might become unstable at extreme densities, causing transitions to new vacuum states that spawn fresh cosmic cycles. Alternative models propose that dark energy might decay or change its properties over time, leading to different cosmic destinies. Some universes might undergo cyclic evolution, expanding and contracting repeatedly through collisions between higher dimensional branes. Others might transition to new phases of inflation, creating vast regions of new space that could spawn their own collections of bubble universes. The study of dark energy has also revealed connections to fundamental physics that could help us understand the nature of space and time themselves. If dark energy represents the energy of quantum fluctuations in empty space, then measuring its properties provides direct information about the quantum structure of spacetime at the largest scales. This could help us understand how gravity behaves in the quantum realm and how space and time emerge from more fundamental information theoretic processes. Dark energy might also be connected to the holographic principle we explored earlier. If our universe is a holographic projection from a lower dimensional boundary, then dark energy might represent the energy cost of maintaining this holographic mapping. Different multiverse configurations might require different amounts of energy to sustain their holographic structure, leading to the observed diversity of dark energy densities. As we contemplate this mysterious force that dominates our cosmos, we're reminded that the universe continues to surprise us with phenomena that challenge our deepest assumptions about reality. Dark energy forces us to confront the possibility that the space around us is filled with invisible energy that could provide our first glimpse into the larger multiverse structure that contains our cosmic home. In the quantum realm of computation, a single quantum bit can exist in a superposition of 0 and 1 simultaneously, allowing quantum computers to process information in ways that seem almost magical compared to their classical counterparts. But according to the many worlds interpretation, these quantum computers might be doing something even more extraordinary. They might be harnessing the computational power of parallel universes, performing calculations across multiple realities simultaneously. The story of quantum computing begins in the 1980s, with physicist Richard Feynman's observation that simulating quantum systems on classical computers becomes exponentially difficult as the size of the quantum system grows. A classical computer trying to simulate just 300 interacting quantum particles would require more memory than there are atoms in the observable universe. Feynman proposed that the solution might be to use quantum systems themselves as computers, naturally processing quantum information without the exponential overhead. The key insight is that quantum systems can exist in superpositions of multiple states simultaneously. While a classical bit can be either 0 or 1, a quantum bit, p-bit, can be both 0 and 1 at the same time, with specific probability amplitudes for each state. Two qubits can exist in superpositions of all four possible combinations: 0, 0, 0, 1, 10, and 11. 3 qubits can represent 8 states simultaneously, and n qubits can represent 2 circumflex n states. This exponential scaling means that a quantum computer with just 300 qubits could, in principle, represent more states than there are atoms in the observable universe. When such a system performs a quantum computation, it manipulates all these superposed states simultaneously, effectively performing an enormous number of parallel calculations. The challenge is extracting useful information from this vast parallel computation when quantum mechanics only allows us to observe a single outcome. David Deutsch, one of the pioneers of quantum computation, proposed that the many worlds interpretation provides the most natural explanation for quantum computing's power. According to Deutsch, when a quantum computer performs a calculation, it's not just manipulating superposed states in a single universe, it's coordinating calculations across multiple parallel realities. Each branch of the universal wave function performs part of the computation, and quantum interference allows information to flow between branches in ways that enhance the probability of obtaining correct answers. Consider Shor's algorithm, the quantum algorithm that can factor large numbers exponentially faster than any known classical algorithm. When a quantum computer runs Shor's algorithm, it creates a superposition over all possible factors of the target number. In the many worlds picture, different branches of reality explore different potential factors simultaneously. The algorithm uses quantum interference to amplify the probability of measuring the correct factors while suppressing incorrect ones. The final measurement collapses the superposition, revealing the factors that emerged from this vast parallel search. This interpretation suggests that quantum computers are the first technology to explicitly harness the multiverse for practical purposes. Every quantum calculation draws on computational resources that extend far beyond our single universe, accessing a form of parallel processing that spans multiple realities. The quantum advantage in computation might literally come from borrowing computational power from our parallel selves in other branches of the wave function. Recent demonstrations of quantum supremacy have provided experimental evidence for this extraordinary computational power. In 2019, Google's Sycamore quantum processor performed a specific calculation in 200 seconds that would have taken the world's most powerful classical computer approximately 10,000 years. While this particular calculation was designed to showcase quantum advantage rather than solve a practical problem, it demonstrated that quantum computers can indeed access computational resources unavailable to classical systems. The quantum computation was essentially sampling from a probability distribution that's exponentially difficult for classical computers to simulate. The 53-qubit Sycamore processor created superpositions involving 2 circumflex 53 is approximately equal to 10 circumflex 16 quantum states, performing operations on all these states simultaneously. From a many-worlds perspective, this involved coordinating calculations across 10 circumflex 16 parallel universes, each contributing to the final probability distribution that was sampled by the measurement. Quantum error correction reveals another deep connection between quantum computing and the multiverse. Quantum information is extremely fragile, easily destroyed by environmental interference that causes decoherence. But quantum error correction codes can protect quantum information by distributing it across multiple qubits in clever ways that allow errors to be detected and corrected without destroying the quantum superposition. These error correction codes work by creating quantum entanglement between different qubits, spreading the logical quantum information across the entire system. In the many-worlds interpretation, this entanglement connects the different branches of reality where the computation is taking place. Error correction ensures that all branches remain synchronized and that errors in some branches don't corrupt the overall computation. It's as if the error correction code maintains communication between parallel universes to ensure they're all working on the same problem. The development of quantum algorithms continues to reveal new ways to exploit multiverse parallelism. Grover's algorithm can search unsorted databases quadratically faster than classical algorithms by using quantum superposition to query multiple database entries simultaneously. Quantum machine learning algorithms can process exponentially large datasets by encoding information in quantum superpositions and using quantum interference to extract patterns. Each new algorithm discovers new ways to coordinate computation across the branching structure of reality. The practical implications of multiverse-powered quantum computing are staggering. Cryptographic codes that would take classical computers longer than the age of the universe to break could be solved by quantum computers in reasonable time. Drug discovery could be revolutionized by quantum simulations that model molecular interactions with perfect accuracy. Climate modeling, financial optimization, artificial intelligence, countless fields could be transformed by access to multiverse-scale computational resources. But quantum computing also raises profound questions about the nature of computation and information itself. If quantum computers are indeed harnessing parallel universes, what does this say about the fundamental nature of information processing? Are all computations ultimately quantum mechanical? Is classical computing just a special case where we ignore the multiverse and focus on a single branch? Some interpretations suggest that even classical computers might be performing quantum computations in ways we don't usually recognize. Every classical bit flip involves quantum processes at the level of individual electrons and atoms. The appearance of classical deterministic computation might emerge from averaging over quantum processes that are actually exploring multiple possibilities simultaneously. Classical computation might be quantum computation with very strong decoherence that forces the system into a single branch. The future of quantum computing promises even deeper connections to multiverse physics. Topological quantum computers would use exotic quantum states called enyons that are naturally protected from certain types of errors. These systems might provide more direct access to the multiverse by maintaining quantum coherence over larger scales and longer times. Quantum internet networks could create distributed quantum computers that span the globe, potentially opening new channels for multiverse communication. As we contemplate these quantum machines that seem to reach across realities to solve problems, we're witnessing the birth of truly multiverse technology tools that explicitly harness the parallel processing power of infinite realities to expand the boundaries of what's computationally possible. In an infinite universe, every possible arrangement of matter must eventually repeat. This mathematical inevitability leads to one of the most unsettling implications of multiverse theory. Somewhere out there, perfect copies of you are living lives identical to yours in every detail. These doppelgangers raise profound questions about the nature of identity, uniqueness, and what it means to be an individual in a cosmos of infinite possibility. The mathematics behind this startling conclusion comes from basic probability theory applied to infinity. Consider a volume of space the size of your room. There are a finite number of ways to arrange all the atoms within that volume, an enormous number, but still finite. If space is infinite and matter is distributed roughly uniformly throughout the universe, then every possible arrangement of atoms within a room-sized volume must occur infinitely many times. The distance to your nearest identical copy depends on how precisely we define identical. If we require an exact quantum state match for every particle in your body, the distance is roughly 10 circumflex, 29 meters away, a number so vast that it defies comprehension. But if we allow for small differences that don't affect your macroscopic properties or consciousness, your nearest close copy might be much nearer, perhaps only 10 circumflex, 10 meters away. These calculations assume that we live in a level I multiverse infinite space beyond our cosmic horizon, all governed by the same physical laws. But the other levels of multiverse theory multiply the doppelganger possibilities exponentially. In the level 3 quantum multiverse, every quantum event that could have different outcomes creates branches where different versions of you experience different results. Rather than being separated by vast distances, these quantum copies of yourself exist in parallel realities, accessible through the branching structure of the universal wave function. The philosophical implications are staggering. If perfect copies of you exist, experiencing identical thoughts and making identical choices, what makes you uniquely you? The problem becomes even more acute when we consider that there aren't just one or two copies, but infinitely many. In an infinite multiverse, there are infinitely many versions of you reading these exact words at this exact moment, thinking these exact thoughts about doppelgangers and infinity. Some of these copies live in universes almost identical to ours, differing only in events beyond your local environment. Others inhabit realities where small quantum differences early in cosmic history led to slightly different configurations of matter and energy. Still others exist in universes with different physical constants, where the fundamental forces have different strengths, but somehow still allow for structures complex enough to support consciousness. The doppelganger paradox intensifies when we consider your future choices and experiences. In the many worlds quantum multiverse, every decision you could possibly make will be made by some version of you in some branch of reality. The career you don't pursue, the relationship you don't start, the words you don't speak, all these unlived possibilities are being lived out by your quantum copies in parallel realities. This leads to what philosophers call the measure problem in multiverse theory. If infinitely many versions of you exist, experiencing every possible variation of your life, what determines which version you consider to be the real you? Why do you experience this particular sequence of events rather than one of the infinite alternatives? The measure problem asks how to assign probabilities, or weights, to different branches of the multiverse, when all branches are equally real from the perspective of the universal wave function. Some proposed solutions to the measure problem focus on the concept of typical observers. Even in an infinite multiverse, some types of experiences might be more common than others. Perhaps you should expect to find yourself in a typical universe with typical experiences simply because typical scenarios occur more frequently than atypical ones. But defining what counts as typical requires solving the very problem we're trying to address. The Boltzmann brain paradox adds another layer of strangeness to the doppelganger problem. Ludwig Boltzmann realized that if the universe exists for an infinitely long time, thermal fluctuations will occasionally create complex structures, including brains with memories and consciousness. These Boltzmann brains would have the experience of being conscious observers with detailed memories of a past that never actually occurred. Their memories would be the result of random fluctuation rather than genuine history. In an infinite multiverse, Boltzmann brains might vastly outnumber genuine observers like ourselves, who evolved through natural processes. This creates a disturbing possibility. You might be a Boltzmann brain with false memories of a life that never actually happened. The memories you have of childhood, education, relationships, and experiences might be nothing more than the accidental result of a rare quantum fluctuation that created a brain with pre-installed false memories. The problem becomes even more troubling when we consider that Boltzmann brains could spontaneously form with any possible set of memories and experiences. There could be Boltzmann brains that remember being Napoleon, Einstein, or fictional characters like Sherlock Holmes. There could be Boltzmann brains with memories of living in universes with completely different physics or histories. If such random observers outnumber genuine evolved observers, we would be more likely to be Boltzmann brains than real people. Recent work in cosmology has tried to address the Boltzmann brain problem by considering the detailed dynamics of cosmic evolution. In many cosmological models, the universe will eventually reach a state where Boltzmann brains become common, but during the current epoch, genuine observers should vastly outnumber random fluctuations. The key is to compare the total number of observations made by evolved observers during the universe's history with the total number of observations made by Boltzmann brains over all of cosmic time. The doppelganger paradox also raises questions about moral responsibility and personal significance. If infinitely many versions of you exist, making every possible choice, what's the moral weight of any particular decision? Some philosophers argue that this makes every choice infinitely important, since every decision determines which branch of the multiverse you personally experience. Others suggest it makes choices meaningless, since every alternative is being explored by other versions of yourself. The concept of quantum suicide illustrates these moral paradoxes in extreme form. If the many worlds interpretation is correct, then every time you face a potentially fatal situation with quantum uncertainty, reality branches into outcomes where you survive and outcomes where you die. From your subjective perspective, you would only experience the branches where you survive, potentially leading to the illusion of quantum immortality. But this raises troubling questions about risk-taking behavior and the meaning of mortality in a multiverse where some version of you always survives. As we contemplate the possibility of infinite selves living infinite variations of your life, we're forced to reconsider fundamental assumptions about identity, uniqueness, and purpose. Perhaps what makes you special isn't your uniqueness, since perfect copies of you exist throughout the multiverse, but rather your particular perspective, your specific conscious experience of being you in this moment, in this branch of reality, contemplating these very questions about your place in the infinite cosmos. The paradoxes of time travel have fascinated scientists and storytellers for generations, but the multiverse offers elegant solutions to these temporal puzzles that transform impossibilities into inevitable consequences of quantum mechanics. Rather than creating contradictions that tear apart the fabric of causality, time travel in a multiverse creates new timelines, new branches of reality, where altered histories can unfold without paradox. The most famous temporal paradox is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, how could you have been born to make the trip in the first place? Classical thinking suggests this creates a logical contradiction, but your existence both enables and prevents your own birth. But the many worlds interpretation dissolves this paradox by allowing multiple, consistent timelines to coexist. When you travel back in time, you don't enter your own past. You enter a parallel universe that happens to be synchronized with your past. Your actions in this parallel timeline can alter its history without affecting the original timeline where you were born. In one branch of reality, your grandparents never meet and you're never born. In the original branch, your grandparents do meet, you are born, and you eventually travel back to create the alternate timeline. Both branches are equally real and equally valid. This branching timeline model emerged naturally from the mathematical formalism of quantum mechanics applied to general relativity. Einstein's theory allows for closed time-like curves, paths through space-time, that loop back to their own past. These curves could theoretically be created by exotic configurations of matter and energy, such as traversable wormholes, rotating black holes, or cosmic strings moving at relativistic speeds. But quantum mechanics introduces fundamental uncertainties that affect any time travel scenario. When you travel back and interact with the past, those interactions are quantum mechanical processes, subject to superposition and entanglement. Just as the double-slit experiment creates multiple realities corresponding to different possible paths for a particle, time travel creates multiple realities corresponding to different possible alterations of history. The Novikov self-consistency principle provides an alternative approach to resolving time travel paradoxes. Proposed by Igor Novikov in the 1980s, this principle suggests that the universe somehow conspires to prevent paradoxes from occurring. Any attempt to change the past will be thwarted by events that ensure history unfolds exactly as it always did. If you try to kill your grandfather, you'll always fail. Perhaps your gun will jam, or you'll change your mind, or you'll discover he wasn't actually your biological grandfather. But the many worlds framework suggests a different interpretation of self-consistency. Rather than the universe actively preventing paradoxes, quantum mechanics naturally selects for consistent timelines through the process of decoherence. Branches where paradoxes would occur become quantum mechanically unstable and effectively disappear from the multiverse, while self-consistent branches remain stable and observable. Recent research in quantum gravity has revealed new connections between time travel and the structure of space-time itself. In the holographic principle, the interior of a region of space is encoded on its boundary, suggesting that time travel might involve manipulating information on the boundary to affect the interior bulk space. Time loops could be created by carefully orchestrating quantum entanglement patterns on the holographic boundary. Loop quantum gravity, an alternative approach to quantum gravity, suggests that space-time itself is quantized at the Planck scale. This discrete structure of space and time might naturally prevent certain types of time travel paradoxes by making exact repetition of events impossible. Even if you could travel back in time, the quantized nature of space-time would ensure that you enter a slightly different quantum state than the one you left. String theory offers perhaps the richest framework for understanding time travel in the multiverse. The extra dimensions of string theory provide numerous ways to create closed, time-like curves through higher dimensional shortcuts. Brains moving through the bulk space could create time machines that connect different points in the four-dimensional space-time we experience. Each passage through such a time machine could potentially access different regions of the string landscape, allowing travel not just through time, but through the space of possible physical laws. The delayed choice quantum eraser experiments we discussed earlier reveal that quantum mechanics already incorporates a form of retrocausality. Our choice of measurement in the present seems to retroactively determine what happened in the past, suggesting that the future can influence the past through quantum correlations. This quantum retrocausality might be a limited form of time travel that's already operating in nature. Some interpretations of quantum mechanics go even further, suggesting that consciousness itself might have time travel capabilities. If consciousness plays a fundamental role in wave function collapse, then conscious choices in the present might influence the past through quantum correlations that extend backward in time. Every decision you make might be subtly affecting past events through quantum channels that transcend our classical understanding of temporal causality. The many interacting worlds theory, developed by Howard Wiseman and others, provides a framework for understanding how information might flow between parallel timelines. According to this theory, nearby branches of the quantum multiverse can influence each other through quantum interactions. Time travel might involve jumping between parallel worlds rather than moving through time within a single universe. Experimental approaches to time travel remain extremely speculative, but some theoretical proposals are beginning to enter the realm of serious scientific consideration. Alcubierre warp drives could theoretically create closed time-like curves by manipulating space-time geometry. Traversable wormholes might be stabilized by exotic matter with negative energy density. Quantum entanglement might enable the teleportation of information backward in time under certain conditions. The practical implications of multiverse time travel extend far beyond science fiction scenarios. If information can flow backward in time through quantum channels, this could revolutionize computation and communication. Quantum computers might be able to solve certain problems by sending their results back in time to influence their own calculations. Communication networks might achieve faster than light information transfer by routing signals through temporal loops. As we contemplate the possibility of navigating through time and parallel realities, we're reminded that the nature of causality itself might be far more flexible than our everyday experience suggests. In a multiverse where all possible timelines exist simultaneously, time travel doesn't violate causality. It reveals the true scope of causal relationships that extend across multiple realities, creating a vast web of interconnected possibilities where past, present, and future merge into a single eternal quantum tapestry. As we stand at the threshold of a new era in physics and cosmology, the multiverse hypothesis is transitioning from speculative philosophy to testable science. Across multiple frontiers, from cosmic observatories, scanning the deepest reaches of space, to quantum computers, probing the foundations of reality, scientists are developing increasingly sophisticated tools to search for evidence of parallel universes and extra dimensions. The next generation of cosmological surveys promises to revolutionize our understanding of cosmic structure and its possible multiverse origins. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey billions of galaxies with unprecedented precision, measuring how dark energy has affected cosmic expansion throughout the universe's history. If dark energy varies across different regions of space, this could provide evidence for the multiverse structures predicted by eternal inflation. The European Space Agency's Euclid mission will map the three-dimensional distribution of galaxies across cosmic time, searching for subtle patterns that might reveal the influence of parallel universes on our cosmic evolution. These surveys will look for signatures of bubble collisions, circular patterns in the cosmic microwave background, or galaxy distributions that could mark where our universe collided with neighboring bubble universes during the early stages of cosmic evolution. Ground-based observatories are pushing the boundaries of precision cosmology even further. The Vera Rubin Observatory, with its unprecedented ability to survey the entire visible sky every few nights, will create the most detailed map of cosmic structure ever achieved. The observatory's legacy survey of space and time will track billions of galaxies, supernovae, and other cosmic phenomena, potentially revealing signatures of extra dimensions or multiverse interactions that were previously too subtle to detect. Gravitational wave astronomy represents another frontier in multiverse research. The detection of gravitational waves by LIGO and Virgo has opened an entirely new window on the universe, allowing us to observe phenomena that are invisible to traditional telescopes. Future gravitational wave detectors, including space-based missions like LISA and next-generation ground-based facilities, will be sensitive enough to detect gravitational waves from cosmic strings, phase transitions between different vacuum states, and possibly even signatures of extra dimensions. The collision of black holes in extra dimensions would produce gravitational wave patterns distinctly different from those we observe in our familiar three-dimensional space. By analyzing the detailed waveforms of gravitational wave signals, scientists might be able to determine whether gravity propagates through hidden dimensions, providing direct evidence for the extra-dimensional spaces predicted by string theory and multiverse models. Particle physics experiments continue to push toward higher energies, where signs of extra dimensions and parallel realities might become visible. The Large Hadron Collider has already probed energy scales approaching those where extra dimensions might manifest, and future colliders could reach even higher energies. The proposed future circular collider would have 7 times the energy of the LHC, potentially revealing supersymmetric particles, extra dimensions, or other signatures of the underlying multiverse structure. High-energy cosmic ray experiments offer another pathway to explore multiverse physics. When ultra-high-energy cosmic rays collide with Earth's atmosphere, they create particle cascades with energies far beyond anything achievable in human-built accelerators. These natural particle physics experiments might reveal signatures of extra dimensions, violations of Lorentz invariance, or other exotic phenomena that could indicate the influence of parallel realities. Quantum technology development is opening new possibilities for testing fundamental aspects of multiverse theory. Quantum computers are becoming powerful enough to simulate quantum systems that classical computers cannot handle, potentially providing insights into the many worlds interpretation and the nature of quantum superposition. As quantum computers scale up to thousands or millions of qubits, they might be able to explore quantum phenomena on scales where multiverse effects become apparent. Quantum sensing technologies are achieving unprecedented precision in measuring fundamental constants and searching for their variation across space and time. Atomic clocks can now detect tiny changes in the fine structure constant or other fundamental parameters that might indicate transitions between different vacuum states or the influence of extra dimensions. Networks of quantum sensors around the globe could detect correlated changes that might signal interactions with parallel universes. Artificial intelligence and machine learning are transforming how scientists analyze cosmological data and search for subtle multiverse signatures. AI algorithms can identify patterns in vast datasets that would be impossible for humans to detect, potentially revealing correlations between cosmic phenomena that point toward multiverse structures. Machine learning techniques are being developed specifically to search for signatures of bubble collisions, extra dimensions, and other multiverse phenomena in observational data. The integration of different observational approaches promises to provide convergent evidence for or against multiverse theories. If parallel universes exist, their signatures should appear across multiple types of observations in cosmic microwave background patterns, galaxy distributions, gravitational wave signals, and particle physics experiments. The combination of evidence from these diverse sources could provide compelling confirmation of multiverse physics. Theoretical developments continue to refine our understanding of what multiverse signatures should look like and how to distinguish them from other phenomena. Advanced computer simulations are modeling the formation and evolution of bubble universes, the dynamics of eternal inflation, and the signatures of extra dimensions with increasing sophistication. These theoretical predictions provide crucial guidance for observational searches and help scientists know what to look for in the vast amounts of data being collected. International collaboration is becoming increasingly important as multiverse research requires resources and expertise that no single nation can provide. Projects like the Square Kilometre Array Radio Telescope, involving dozens of countries, will have the sensitivity to probe cosmic structure on scales where multiverse effects might be detectable. The success of collaborative projects like LIGO and the Event Horizon Telescope demonstrates how international cooperation can achieve breakthroughs that would be impossible for individual institutions. The philosophical and cultural implications of multiverse research are beginning to influence how scientists approach these questions. As the possibility of parallel universes becomes more scientifically respectable, researchers are grappling with questions about the nature of scientific explanation, the meaning of existence, and our place in a potentially infinite cosmos. These considerations are shaping research priorities and influencing how scientists communicate their discoveries to the public. Looking ahead, the next few decades could bring definitive evidence for or against various multiverse theories. The convergence of advanced observational capabilities, theoretical sophistication, and computational power is creating unprecedented opportunities to test ideas that were once considered purely philosophical. Whether these investigations confirm the existence of parallel universes or rule them out, they will fundamentally transform our understanding of reality itself. As we prepare to cross the threshold into a new era of cosmic understanding, we stand poised to answer some of the deepest questions about existence. Are we alone in our universe, or are we part of an infinite ensemble of realities? The answers may be closer than we think.